So how many of the people here are for the 9:30 visit, the CeNSE visit? How many are there? Oh, all of you are here for the CeNSE visit. Okay. So when the team comes, you'll be proceeding to the CeNSE, and take the visit. You have about 20 minutes that we have to use. We can use it, or we can you can just rest, whatever you want. I just played that as a sort of a warm up. I have enough videos to actually satiate you. Okay, I don't want to force it on you. If you want, I can play them. You want to go around? Please go around. Absolutely okay. This is not binding. And those of you who want to stay and you want to watch videos, I can play some very interesting videos for you. Okay? Okay, great. So this one was a start thrower video, a very nice management video on making a difference. Okay, I think we had 20 minutes to that time. Okay, I'll try and play deep dive. A lot of you would be involved in innovation programs in your academic careers, either as faculty or as students. There's a major drive by the government to drive innovation as a culture in our academic society. I'm going to take you through a video called the deep dive, and the deep dive is a very interesting video because it talks of how ideas evolve, how new concepts can be brought out, and then how it can be actualized. So just try and enjoy this for the next, it's about a 12-minute video, and then you can proceed to the CeNSE.
It used to be that you deferred to the boss.
Is it the boss is always going to have the best ideas? Not likely.
Here, nimble fingers, alert minds, and tireless machines.
And it used to be in most companies that chaos was discouraged.
This is where the crazies live. This is where we do our work.
It used to be that you deferred to the boss.
Is it the boss is always going to have the best ideas? Not likely.
Here, nimble fingers, alert minds, and tireless machines.
And it used to be in most companies that chaos was discouraged.
This is where the crazies live. This is where we do our work. It's different.
Good morning. Good morning.
Used to be you were supposed to climb the corporate ladder.
Good morning.
Status is who comes up with the best ideas, not who's the oldest, not who's been with the company longest, not who has that biggest title. If you go into a culture and there's a bunch of stiffs going around, I can guarantee they're not likely to invent anything.
You could stack us up big as you want. That's great. Thanks a lot. We had a great time today.
Well, forget the way it used to be. Tonight, the deep dive. One company's secret weapon for innovation. A lot further along in this broadcast, near the end as a matter of fact, you will hear one of the central characters suggest that we look around. The only thing that's not designed by anybody, he will say, is nature. Actually, you could say the same thing by observing that the only designs that don't require constant modification are the ones we find in nature. But the point is well taken. From the buildings in which we live and work to the cars we drive or the knives and forks with which we eat, everything we use was designed to create some sort of marriage between form and function. Does it work, and can we make it look interesting or attractive? What is truly amazing is how long we tend to put up with things that may not work particularly well or may look especially unattractive simply because we're accustomed to them and because no one has ever suggested redesigning those things. There's an interesting distinction between design and invention. Whoever came up with the idea of dental floss, for example, was an inventor, but the man or woman who put it inside that clever little plastic box that lets you tear off just the right length, that was a designer. Now, how does the process of designing a better product work? And would it be interesting to watch that process? When we first broadcast this program back in February, we weren't at all sure what you would think, but judging by the number of you who ordered video cassettes of the program and the number of people who contacted the industrial product design firm that is featured in this program, you liked it a lot. Here was the premise of the program. We went to IDEO, the product design folk, and said, take something old and familiar, like, say, the shopping cart, and completely redesign it for us in just 5 days. ABC News correspondent Jack Smith tells us what happened next.
9 in the morning, day one, and these people have a deadline to meet.
So welcome to the kickoff of the shopping cart project.
This is Palo Alto, California, in the heart of Silicon Valley, and these are designers at IDEO, probably the most influential product development firm in the world. Designers are the reason TVs have square screens, chairs 4 legs, and toothbrushes nowadays those squishy handles. In fact, it was IDEO that designed those squishy handles. IDEO has designed everything from high-tech medical equipment to the 25-foot mechanical whale in the movie Free Willy, and the first computer mouse for Apple. Smith ski goggles, Nike sunglasses, NEC computer screens. Hundreds of products we take for granted.
This is called the Neat Squeeze toothpaste tube, which...
You invented that? The man who runs IDEO is Dave Kelly, a Stanford engineering professor with a Groucho Marx mustache, a dad of genius, and an approach to innovation that usually works.
Well, thank you, Fred.
But not always.
Thanks a lot. I can show you some products that failed. Came up with this idea called monster shoes, where you take these little monsters and lace them into your shoes, like this. And we built a bunch of them, and I didn't want those either. So.
Mostly what IDEO designs, though, does work, and it works very well. Dave and his design teams create about 90 new products every year.
The point is that we're not actually experts at any given area. You know, we're kind of experts on the process of how you design stuff. So we don't care if you give us a toothbrush, a toothpaste tube, a tractor, a space shuttle, you know, a chair. It's all the same to us. We want to figure out how to innovate by using our process, applying it.
And so for the next 5 days, the team will apply that process to bringing the supermarket shopping cart into the 21st century.
I think first we should maybe all acknowledge that it's kind of insane to do an entire project in a week.
Project leader is Peter Skillman, a 35-year-old Stanford engineer. Project leader because he's good with groups, not because of seniority. He's only been at IDEO for 6 years. The rest of the team is eclectic, but that's typical here. Whitney Mortimer, Harvard MBA. Peter Coughlin, linguist. Tom Kelly, Dave's brother, marketing expert. Jane Fulton-Suri, psychologist. Alex Kazaks, 26, a biology major, who's turned down medical school 3 times because he's having too much fun at IDEO.
Kids climbing up and doing this.
Kids do that?
No.
Safety emerges early as an important issue.
22,000 child injuries a year, which is, and so they're hospitalized injuries. I mean, there are many others.
Not just reported in the store, that's, you actually have to go to the
that's
emergency room.
hospitalized,
Wow.
right.
And theft. It turns out a lot of carts are stolen.
You know, what is the average life of a cart? Does it last 2 years, 5 years, 10 years? And how big is this theft thing?
10 a.m. As the team works, it becomes clear there are no titles here, no permanent assignments.
And the other side says, gives us a lot of help, says, be safe.
Everyone appears to be equal, and they love to mock corporate America.
I'll give you status. I'll give you a big red ball on a post, and that says you're a big guy. If you got a ball, you're a senior vice president. You know, what do I care? The desk, the red ball, it's all the same. In a very innovative culture, you can't have a kind of hierarchy of here's the boss and the next person down, the next person down, the next person down, because it's impossible that the boss is the one who's had the insightful experience with shopping carts. It's just not possible.
According to Kelly, even employees who merely listen to the boss don't add that much either.
So you gotta hire people who don't listen to you, and that, I don't think corporate America wants to hear that right yet.
I think we ought to start making those lists about the kinds of questions that we're going to ask.
The team splits into groups to find out firsthand what the people who use, make, and repair shopping carts really think.
Okay, go.
The problem with the plastic cart is the wind catches it. Yeah. And these things have been clocked at 35 across the parking lot.
Oh, man.
That's actually a pretty good point.
The trick is to find these real experts, and so that you can learn much more quickly than you could by just kind of doing it the normal way and trying to learn about it yourself.
From everything I read, these things aren't that safe either, you know? So probably the seat itself is going to have to be redesigned.
What you're seeing here is the kind of social science, like anthropologists, you know, like you go and study tribes. What is it that they do that we can learn from that will help us design a better cart?
One of the interesting things for me is looking at how people really don't like to let go of the cart, except for the professional shopper, whose strategy is to leave the cart at various places.
In corporate America, many bosses measure whether their people are, the good people or the people who are performing are the ones that they see at their desk all the time. That couldn't be further from the truth. The people who are really getting the information are out here talking to the buzzes of the world, going to meet other experts, much more useful than sitting at your desk.
3:30 in the afternoon, and the group is back at IDEO. There is no let-up.
Each team is going to demonstrate and communicate and share everything that they've learned today. People went off in the four corners of the earth and are coming back with the golden keys to the innovation.
A shopping cart has been clocked at 35 miles an hour traveling through a parking lot in the wind.
We were in the store, 2 hours, and it was truly frightening just to see the kind of stuff going on.
You ought to designate some people to make damn sure that the store owner's point of view is represented.
After 9 straight hours, the team is tired. They call it a day.
So,
everybody cool?
Well, that's great. Thanks a lot. We had a great time today. Get together and start here.
Day 2 and the start of IDEO's unique brand of brainstorming. They call it a deep dive, a sort of total immersion in the problem at hand. IDEO's mantra for innovation is written everywhere. One conversation at a time. Stay focused. Encourage wild ideas. Defer judgment. Build on the ideas of others.
That's the hardest thing for people to do, is to restrain themselves from criticizing an idea. So if anybody starts to nail an idea, they get the bell. You know.
The deep dive begins, and for the next few hours, the ideas pour out and are posted on the walls.
Oh, the blind, the privacy blind. Like when you're buying 6 cases of condoms, no one sees. Nesting is, it sort of has to nest. If it doesn't nest, we don't have a solution.
How about Velcro pants and Velcro seats for the kids, and you just drop them down on there?
Like Velcro seats? Velcro pants for kids?
Yeah, see, you have to have some wild ideas. If then you build on those wild ideas, and they end up being better ideas than if you said, if everybody only came up with sane things, kind of appropriate things, you'd never have any points to take off to build a really innovative idea.
It's organized chaos.
Organized chaos. It's not organized. What it is it's focused chaos.
By 11 a.m., the group begins narrowing down the hundreds of ideas written or drawn on the walls. How? By voting for them.
Vote with your Post-it, not with an idea that's cool, but with an idea that's cool and buildable. If it's too far out there and it can't be built in a day, then I don't think we should vote on it.
Why not have you be the judge? You're the boss.
Because I'm going to be wrong. It's the team that's able to really judge with the best ideas.
Otherwise, ideas wouldn't come out?
That's right. Enlightened trial and error succeeds over the planning of lone genius.
Enlightened trial and error succeeds over the planning of the lone genius. If anything sums up IDEO's approach, that is it. That and the focused chaos that seems to go with it.
I take a point of view, I call it the sport utility vehicle cart.
It is noon. Worried that the team is drifting, what can only be called a group of self-appointed adults under Dave Kelly holds an informal side session.
We don't want to tell them what to build, or else we take away the benefit of the whole thing, right?
What needs should they optimize their solution to?
Yes.
The purpose is to refocus the deep dive.
Maybe we arbitrarily say we could do 5 teams. 4 or 5 teams.
4 or 5.
4 or 5 teams, and we give each team a need area. Hey, can we grab everybody over to the wall here? There has to be a command decision. It becomes very autocratic for a very short period of time in defining what things people are going to work on.
Like it or not, the team is told it will split into groups to build mock-ups, covering 4 areas of concern that have been identified. Shopping, safety, checkout, and finding what you're looking for.
I noticed that toward the end of the process, the adults took over.
Yeah, that's because we have no choice but to stop that cycle. I mean, there's if you don't work under time constraints, you could never get anything done because it's a messy process and go on forever.
While the team starts building prototypes, Dave Kelly takes me on a tour of the rest of IDEO.
What's happening in here is that's a client meeting. That's a first client meeting. That's the first time we met with the client. So we haven't trained them yet. If we took them straight from there into a room where music was blaring and everybody was throwing Nerf darts at each other, that would be a little hard to take. You know, so we're warming them up. But this is where the crazies live. This is where we do our work. It's different. You can tell whether a place is playful in about the first 15 minutes as you walk down the hall. Being playful is of huge importance for being innovative. I mean, if you go into a culture and there's a bunch of stiffs going around, they're not, I can guarantee they're not likely to invent anything.
Invent anything like this futuristic-looking instrument for kids.
So no matter what you do with that thing, you always
sound great.
You always sound good.
You have to make it so that this can happen.
Whoa, it didn't break.
No, it didn't break.
There's a whole department at IDEO devoted to toys. Turns out to be one of its most profitable areas. Fun, too.
So we got these little wings, and no matter what you do, if I get in trouble here, it's always a spiral.
At IDEO, they found that fresh ideas come faster in a fun place. Not only is the furniture on wheels to suit the needs of the moment, but people are encouraged actually to build their own work areas.
And they were designing this space, and they said to me, you know, we'd like to have, you know, $4,000 extra in our budget for a DC-3 wing. And I said, DC-3, you have to have that? And they said, yeah, they have to have it. So
that's a DC-3 wing.
Piece of a DC-3 wing, yeah.
And that's just decor.
That's decor. That's ambiance. You know, that says we're weird, and we're proud of it.
Umbrellas on the ceiling to shade computer screens from direct sunlight. And bicycles on ropes to prevent clutter.
The first guy who hung a bike up on a thing, he didn't come to me and ask me. He didn't ask some facilities person was okay. He tried it. And then, like, he waited and see if anybody complained. If nobody complained, another guy hung a bike up. And pretty soon, everybody's got their bikes up and nobody's complained, right? So it's that whole thing of trying stuff and ask forgiveness, you know, instead of asking permission, is the way people come up with new ideas.
IDEO has such a reputation for innovation that client companies are increasingly asking Dave not just for new products, but also to remake their corporate cultures. You may be looking at the workplace of the future here.
It's one thing to be able to do a product once in a while, but if you can build a culture and a process where you routinely come up with great ideas, that's what the companies really want. Okay, Peter, we're done.
Back at the shop, it is 6 o'clock, and the 4 mock-ups are ready for showing.
Baskets also can be, if you think you will have more volume, baskets can be put in.
A modular shopping cart you pile hand baskets onto. A high-tech cart that gets you through the traffic jam at checkout.
That you could mount a scanner on the shopping cart so that you as the customer, as you pull it off the shelf, would scan each item.
One that's built around child safety, and another that lets shoppers talk to the supermarket staff remotely.
Yeah, where can I find the yogurt?
The yogurt's over in the dairy section.
But the adults, again, decide more work needs to be done before the mock-ups can be combined into one last prototype.
Why don't we have all the carts come up here for a second?
I think you take a piece of each one of these ideas and kind of back it off a little bit and then put it in the, design.
The design is still not there, but there's another motto at IDEO: fail often in order to succeed sooner. And some of the team will be up half the night trying to put together design that finally does work. It is day 5, and Dave Kelly has no idea what the final cart looks like. Only the team does.
If they kind of got their heads down, they don't look at me, I'm nervous. You know, if they say, wait till you see it, then I know we're in good shape. So I'm getting wait until you see it. I think that'll be good.
There it is! There it is! So we took the best elements out of each prototype, designed this entire cart in a day, and then this cart was fabricated in a day with an amazing team of people in our machine shop pulling this off, working in shifts throughout the night.
Wow, I'm impressed.
So are we.
The cart, which is designed to cost about the same as today's carts, is different in every other way. Hand baskets that stack in a metal frame, and major improvements for all.
You just lift the handle up, you drop put the children in, and then you can close the handle right over them, and they instantly have some little bit of a work surface that they can play with.
What do you think?
Well, I'm very proud of the team. I think it's great.
Does this work for you?
Works for me great. Yeah. It's also beautiful. I mean, let's take it over to a local supermarket and see what they say.
Yeah, it works really well.
The cart's wheels turn 90 degrees so it can move sideways. No more lifting up the rear in a tight spot. And you shop in a totally different way.
Rather than taking your cart everywhere you go in the store, through a crowded store like this, it's much more efficient to take a small basket, rush around to where the particular shelves are, and come back and put them here, and treat this as like a center for your shopping.
And with a high-tech scanner, so that in the future you skip the checkout traffic jam.
Here's how you would scan an item. You'd reach over and pick up anything like the salad dressing, and I would scan it, and if I want to accept that item, I would just press plus and then drop it in my basket.
Because stores don't yet have those high-tech scanners the team designed, checking out today means doing it the old-fashioned way. But the bags are hung on hooks on the cart's frame. Remember, there is no basket here.
Why get rid of the big basket?
The basket is tyranny. The basket is tyranny because it's not really needed. If all your stuff ends up in bags, why need the basket in the first place?
Talk to me about theft.
There's no value in this cart without the basket because you can't carry anything in it. It's useless to anybody. You can't use it as a barbecue.
So it's not going to get stolen.
That's right.
So this ought to appeal to store owners then.
Yes.
I love it. I think it looks great.
At first, I was a little shocked, but I think you have some fantastic ideas here. It needs a little refining, but I think that it's great. I mean, we would want them.
It makes us feel great. And she also gave us some really good comments about how we can make this thing better.
Just wherever you are, look around. The only thing that's not designed by somebody is nature. So the trees are not designed by us, but everything you see, every light fitting, every flower vase, every scale, every stand for fruit, everything is designed, has to go through this kind of process. And they can do a better or worse job of innovating or improving, but everything is designed. It has to go through this process.
It wasn't this effortless, oh my God, so that's how it works thing that I saw there. It was actually hard work.
It's a lot of hard work. We all love it, so it doesn't look like it's hard work, but it's a lot of hours.
A lot of hours. Also, an open mind, a boss who demands fresh ideas be quirky and clash with his, a belief that chaos can be constructive, and teamwork, a great deal of teamwork. And these are the recipe for how innovation takes place. This is Jack Smith for Nightline in Palo Alto, California.
I'll be back with a brief update on our story in just a moment. Incidentally, the Nightline shopping cart won a silver award in the Industrial Design Excellence Awards, and there's talk now of developing it commercially. That's our report for tonight. I'm Ted Koppel in Washington. For all of us here at ABC News, Good.
Okay, we are ready to send the industry and the faculty teams for the CeNSE visit. So can the industry and the faculty just proceed outside, and Rashika and the CeNSE team will take you there. So the visit will actually start closer to 10, but you have to proceed right now so that you can complete the gowning and whatever other processes they require. The students should stay back. For students, they have videos on CeNSE that we'll play, and we'll have other videos that we'll run through till. Okay, those who gave the names, yesterday, they can all go. Are there students? If the students are given the names, those names. That one. Oh, hold on. There is an issue coming up. There is a limit of up to 40 people. Prem, there is a limit of up to 40 people. And 40 people will also be divided in batches. Please, for those who have not registered, my suggestion is stay back. We have got other videos.
Yeah, we can
Only industry and faculty? Only industry and faculty. They are saying only industry and faculty, please. I'm sorry, but they are only letting industry and faculty in. Please stay back. We have the CeNSE videos, and they are going to be just as functional. And we will also have the commercial silent training video, so we can actually be totally deployed. Sir, aap lगा लीजिएगा. Please go ahead. Thank you for your patience on this.
Ever wondered how the chips that run your computers are made? It's a complex process that is carried out in an environment called a clean room. We are standing here today in one such clean room at the Center for Nanoscience and Engineering in the Indian Institute of Science. You see scientists working around me in clean room suits. They prevent our skin flakes from contaminating the room. This is a class 1000 clean room, meaning that the number of dust particles greater than 0.5 microns in size in 1 cubic meter is less than 1000. Outside the room, there are 35 million particles or more in the same volume. Yes, we breathe all that. The air that enters the room is put through filters to remove 34,999,000 particles to make it clean, and exits through these holes in the floor. The chips that run your computers are made by robots. We will see how chips are made manually to understand the process. We start with a silicon wafer. This wafer is first put through a rigorous cleaning procedure and is the substrate on which devices will be made. A typical step in device processing is to deposit material on the wafer in thin film form In this case, we are going to insert the wafer in a chemical vapor deposition reactor that allows deposition of materials using gas phase reactions. After a few hours, the wafer emerges and is coated with the material of interest. The foundation has been laid. It's now time to build our device on this wafer. It involves many steps with a mask defining every step. This is called a process flow. The entire mask set is designed and printed in advance. We will take you through the first two mask steps. The first step involves putting down metal pads at specific points on the wafer surface. A mask is first created on a chrome-plated glass plate. It is now time to transfer the pattern that is there on the mask plate onto the wafer surface. To do so, we will now travel from the chemical vapor deposition reactor to the lithography bay. Lithography means writing with light. You will see that the bay here is flooded in yellow light. It is ultraviolet, UV-free illumination. We will first spin coat a special chemical called a photoresist or PR on the wafer. It is special because it's chemically altered by UV light. After the PR has dried, the coated wafer and the mask are loaded onto a mask aligner and illuminated with UV light. Only those areas that are not masked off are exposed. After exposure comes development. The wafer is dipped in a chemical that dissolves our special chemical, the PR, only from those regions exposed to UV light through the mask. It's only these regions that the PR is chemically altered and hence made soluble in the developer. Voila! We now have a pattern transfer. In these regions from where the PR has been dissolved out and where the CVD material deposited surface is now seen, the metal pad pattern we desire in step 1 will be deposited. Now, you should be able to answer the question as to why the room is bathed in UV-filtered yellow light. The wafer with a patterned photoresist now travels to the metal deposition bay, where it is loaded in a physical vapor deposition unit. Metal is vaporized and it coats the entire surface of the patterned wafer, both those covered with photoresist and the exposed wafer areas. The wafer is now subjected to a process called lift off to get rid of the photoresist coated metal. It is dipped in a solvent that dissolves the photoresist and in the process removes or lifts off the metal on top of it. The metal that is deposited on the wafer surface stays in form of the pattern that was desired. The first mask step we had embarked on, what appears to be a long time ago, is now over. Devices require that other patterns be transferred, but with a specific relation to the first one. To do so, the wafer with the first pattern is again coated with PR, and the entire process is repeated but with mask 2. Mask 2 is aligned using features on the surface of the wafer. This is the most critical step, as any misalignment here means that wrong electrical connections will get made. The device or circuit will then not work properly. The PR is exposed and the metal is deposited again. Post liftoff, the second pattern with a definite relationship to the first one is now realized. We have now gone through 2 steps. Similar processes are repeated to finish the device. This process has taken many masks, many different pieces of equipment, many material deposition steps, not just metals, and many hours of work. Time now to test the device we made. The devices that run our laptops and cell phones are extremely small, nanometers to micrometers in size. You can fit more than 1,000 of them in a cross-section of human hair. The features we just made are so minute that to contact them, to make electrical connections, we need very fine probes. The wafer with the completed devices is loaded onto a probe station, and the exact device to be tested from the thousands that we made on a single wafer is contacted. Voltages are applied, currents are measured. Looks like our transistor is working. The wafer we have just processed is divided into squares, along which we will now cut using a diamond blade to realize what are called dies. Each die has the devices or circuits we just realized using our 10 mask process. After dicing, the dies are now first mounted onto a package, and then wires are bonded to the very small features so that the external world can make electrical connections with the circuits we have made. The package is now closed. These are the components you see on any PCB inside an electronic device. The life of the wafer now ends, and that of the device begins.
So good morning everybody, and yesterday I talked to you about the silane gas, and what was the unique thing about silane gas? Pyrophoric, catches fire just in the process of touching air. So how do you actually handle silane commercially? How do you actually handle silane in real life? Because if it is going to catch fire the moment it is exposed to air, then it is so dangerous. How do you actually control this? I'm going to take you through a 30-minute video. This is going to actually be a commercial silane training. Please take time out to get a feel of it. This is the gas which possibly burned down SCL Chandigarh. Okay, so this is again a very interesting area of specialization, handling such gases. Let me try.
Welcome to this video version of the REC Silicon Silane Training and Operations Manual. It is designed to be used in conjunction with your printed version of the manual. If there are any points that you're unclear on, please refer to that document or contact the numbers shown at the end of this presentation. REC Silicon is a best-in-class silicon materials manufacturer and a major player in the photovoltaic, LCD display, and semiconductor industries. As the world's largest manufacturer of silane gas, REC Silicon is unmatched in manufacturing, handling, packaging, and transporting silicon gases. We maintain our unique position with multiple manufacturing and loading facilities, as well as a large storage capacity at each plant, and a service-driven philosophy that puts our customers' success first. REC Silicon ships bulk silane worldwide. The container types available for silane shipment are cylinders, tonners, and 10-foot, 20-foot, triple 20-foot, and 40-foot ISO modules. REC Silicon has the world's largest silane gas ISO module fleet. Silane is a highly reactive chemical that self-ignites in contact with air and requires special handling. This video will cover 4 areas. First, we'll outline the general properties of silane gas. Second, we'll go over the layers of protection needed at a facility for the safe handling practices of silane. Third, we'll discuss receiving, connecting, and operating an ISO module. And then finally, we'll detail how to disconnect and return an ISO module to REC Silicon. Once again, this video is an overview. For more detailed information, please refer to your silane training and operations manual or talk to your REC Silicon Gases representative. Silane gas consists of an atom of silicon combined with 4 atoms of hydrogen. Not found in nature, it exists only under very specific conditions and possesses some unique chemical properties. At room temperature, silane is a gas, but silane can liquefy under normal ambient conditions at temperatures lower than its critical point and from a large pressure drop, where the Joule-Thomson expansion cooling can cause a drop in temperature to the point that silane will start to condense. Silane's critical point is 26 degrees Fahrenheit, or negative 3.4 degrees Celsius. Above this temperature, silane can only exist as a gas. Below this temperature, silane's phase depends upon temperature, pressure, and density. Extra care needs to be taken when handling liquid silane. Therefore, an awareness of silane's critical point is very important in day-to-day operations. In order to handle silane safely, you need to understand its hazards. The primary hazard of silane gas is its flammability. And while there are many common examples of flammable gases like natural gas, propane, or hydrogen, silane is unique because it's pyrophoric. The term pyrophoric means that when it is released into the air, it can ignite without an ignition source. This pyrophoric behavior is not typical of most flammable gases. As an example, propane burners or heaters require a pilot flame, sparks from a flint striker, or an electrical discharge to start the propane gas burning. When silane is released into the air, it may ignite without an ignition source. Another thing that makes silane unique is its very broad flammability limits. Flammability limits are the concentration range of the flammable gas when mixed with air that will support combustion. Propane, for example, has flammability limits of around 2% to 10%. If it's below 2%, it's too lean to burn. If it's above 10%, it's too rich to burn, even with an ignition source. By comparison, silane's flammability limits are 1.4% to 96% when mixed with air, and it maintains its pyrophoric nature between 2.5% and 96% over nearly all of its flammability range. You can see from this comparison of silane with propane, a gas that most people consider relatively flammable, that silane is perhaps better characterized as an extremely flammable gas. While released silane is dangerous when it ignites and it burns, it can be even more dangerous when it doesn't. Silane is an unpredictable gas and does not always ignite immediately. Spontaneous ignition depends upon the geometry of the release, line pressure of the release, and the environment it is released into. For example, silane may not ignite immediately if it is released from high pressure at high velocity. When the released silane does ignite, sufficient silane gas may have accumulated that an explosion can occur. Silane's unpredictability means that even under the same release conditions, different results may occur. There are 5 things that can happen. 1. Nothing. 2. Brown or white powder formation. 3. Intermittent popping sounds. 4. Immediate ignition fire. And 5. Delayed ignition fire or explosion. The explosion could be even more violent if it occurs in full or partial confinement, such as inside a building or a cabinet with insufficient ventilation. In addition to silane's flammability and explosion hazards, silane can be explosively reactive with other chemicals in classes of chemicals. For example, silane is explosively reactive with oxidizers, such as nitrous oxide or hydrogen peroxide, and halogens, such as fluorine, chlorine, bromine, and with certain halocarbons, such as CFC12 or CFC22. This list is not intended to be all-inclusive. In general, silane should not be mixed with any other chemical unless you are absolutely sure of its stability and reactive behavior. Otherwise, the results could be deadly. Correct handling of silane is critical for both your safety and your company's success. So here are a few things to keep in mind when working with such a highly reactive substance. Before performing any work, wear the appropriate personal protective equipment, or PPE for short. Proper PPE can help prevent injuries from silane hazards such as flames, radiant heat, thermal burns, and hearing damage. Proper silane PPE includes fire-resistant clothing, thick leather gloves, a hard hat, safety glasses, and safety shoes. When breaking into a silane container or process, you should always assume silane is present. An additional PPE should be worn, such as earplugs, fire-resistant hood, and face shield. Hearing protection is necessary because even tiny releases can cause pops or small explosions that can be harmful to your hearing. When simply operating equipment that contains silane, it is not necessary to wear the face shield, flame-resistant hood, or the hearing protection. However, when breaking into a process, always assume that silane is present. How the silane end-use or transfer facility is designed and constructed can significantly impact safe operations. The facility should be designed to the best engineering practices according to ANSI and the CGA G13 standards, and should be reviewed by a team of experts. With this in mind, there are several key areas to pay attention to. These include security, location, construction, detection, emergency shutdown, mitigation, and emergency response. Access to the facilities should be restricted to qualified personnel only. The facilities should be manned or monitored 24 hours a day. The facility should be located outdoors, and the recommended setback distances should be accounted for. The facility should be located away from occupied buildings, high traffic roads, physical hazard fluids, and incompatible materials, or acceptable engineering barriers should be installed. The system should be constructed using stainless steel tubing, valves designed for silane service, welded connection fittings, or otherwise acceptable mechanical connections, such as VCR or DIS. Silane is typically handled as a gas. Handling silane as a liquid requires special precautions, because if liquid silane is trapped into a confined area and then vaporizes or expands, overpressurization can occur. To mitigate this hazard, handling silane as a liquid should be avoided. Engineering controls such as heat trace should be installed into the piping system to ensure that silane stays above its critical point, 26 degrees Fahrenheit or minus 3.4 degrees Celsius. The facility should be designed with detection safety systems such as silane detectors set to shut down the supply of silane at 10 parts per million, and flame detectors that are also interlocked to shut down the supply of silane. Additional safety measures can be used for additional risk reduction for outdoor facilities, but must be taken if the facility is located indoors. These include explosion control, remote video monitors, smoke detectors, heat detectors, and oxygen sensors. Automatic shutdown and mitigation should be provided if silane or fire is detected. A remotely located, manually activated shutdown control should be provided, and additional shutdown devices should be located at each exit. Shutdown control needs to be provided in order to stop the flow of gas at its supply and at its point of use. Adequate ventilation is always important, but it is especially critical in the event of a silane release. An indoor facility should be equipped with a system that provides constant airflow of 150 feet per minute or 0.8 meters per second across all mechanical connections, and enough ventilation for 6 air changes per hour or 1 cubic foot per minute of floor area. Because fire is the primary danger of silane, adequate fire emergency equipment is vital. Working fire hoses, extinguishers, and automatic deluge systems are key components. Fire equipment must be tested regularly. If it doesn't work the first time, there may not be a next time. The facility should be designed to vent normal flows and concentrations of silane, and there should be a plan in place to address venting or transfilling emergency quantities of silane. Vent lines should be continuously purged with an inert gas at a velocity of 1 foot per second to prevent oxygen from entering the vent line. The inert gas system should have a low pressure alarm to indicate a loss of supply, or an auto purge system requiring certain pressure set points to complete an operation. Any facility that uses silane or other hazardous materials must have a detailed emergency response plan. Such a plan spells out who's responsible and the procedures for directing and supporting emergency operations, communicating inside and outside the plant, ensuring rescue and medical services if needed, and handling other issues such as plant security and notifying regulatory agencies. All emergency responders, including off-site responders, need to be trained on silane, the containers, and the site layout. Appropriate equipment needs to be used, including bunker gear and SCBA, or self-contained breathing apparatus. In the event of an emergency, every silane facility needs a well-maintained alarm system and fast, easy-to-use communication systems. Communication systems such as phones, radios, and intercom systems are all cost-effective ways to allow a fast response, when a few minutes can make the difference between a small incident and a big problem. Facilities should have an evacuation plan in place, and workers and emergency responders should be drilled regularly to ensure the swift response that can save lives and protect property.
They're designed for safety for the responders that are inside the hot zone.
The basic precautions for working with silane are these. First, treat all silane mixtures as potentially dangerous and evacuate personnel from the surrounding area. Second, cool the containers with flooding quantities of water and allow silane fires to burn out. Do not try to extinguish them in any way, as that could lead to increased concentrations of silane and a possible explosion. Third, control the area around the fire with water, carbon dioxide, or a dry chemical extinguisher. Fourth, do not try to isolate an unignited silane release while you are in the area. Instead, use remote isolation. And lastly, never use halon fire extinguishers on a silane fire. Now let's take a look at the silane ISO modules themselves and the components you'll be working with. Each ISO module contains 8 to 12 high-strength carbon steel tubes inside a steel frame, all designed to meet legally mandated safety requirements. At both ends of each tube, a bull plug assembly is threaded into the steel tube. The bull plug houses a tube valve and, for some countries, a pressure relief device, or PRD for short. The PRD is designed to vent silane away from the tube and manifold in case of a fire. It is comprised of a high-strength stainless steel body that's welded onto the bull plug. The PRD is designed so it only releases in a fire scenario where there is both high pressure and high temperature. Inside the device, pressure relief is provided by a rupture disc, which gives way when pressure reaches between 3,700 and 4,000 psi-G, and a lead plug that melts at 165 degrees Fahrenheit or 74 degrees Celsius. After both the rupture disc bursts and the lead plug melts, the silane escapes through the tube vent, which is routed above the tubes and away from the manifold, allowing for less damage and better control. As you can see, both high temperature and high pressure, the conditions of a fire, are required to activate the PRD. The second connection on the bull plug assembly, the tube valve, allows silane to the manifold and ultimately to the manufacturing process. When the tube valves are open, they allow silane into a stainless steel tubing manifold, which connects all the tubes. Here the manifold valves allow the flow of silane to the master inlet-outlet valve and onto the customer process connections on a tube-by-tube basis or all tubes at once depending on your process. The manifold valves should not be used to regulate the flow of silane. They should either be closed or open. Flow regulation should be accomplished by using valves or an RFO, a reduced flow orifice, built into your manufacturing process. This system of valves allows operators to isolate individual tubes during shipment and use and during emergency situations. An automatic shutdown limits the source of silane in the event of a leak. What do you do when an REC silicon ISO module arrives at your manufacturing facility? Let's follow a team of silane operators now as they prepare to receive a shipment of silane and operate the ISO module. Prior to performing any work, review and follow the correct procedures and wear the appropriate PPE. Next, inspect the incoming ISO module to make sure it is carrying the proper placarding. Placards indicate the hazard and contents of the ISO module and are required by law. Be alert for physical damage to the ISO module tubes, frame, doors, and ISO module chassis. If you find any denting or deformation of the ISO module, you should stop and notify REC Silicon immediately. Light or superficial corrosion and damage need not be reported. Check to make sure that the car seal is in place on both the front and rear manifold doors, and that the car seal has not been tampered with. Carefully inspect the ISO module manifold content label ticket, which will tell you the manifold helium pressure and the loaded silane tube pressure. Note that the silane tube pressure can vary depending on the temperature. If the ticket is not in order, report this discrepancy to REC Silicon immediately. Verify that all manual valves are wire-tied and that the manifold's inlet and outlet CGA caps are present. Next, visually inspect the PRDs and bull plugs on both front and rear manifolds for evidence of silane leakage, as well as the valves and fittings on the rear manifold. The presence of either a fine white powder, silicon dioxide, or fine brownish powder, silicon monoxide, indicates that silane leakage has occurred and should be reported to REC Silicon immediately. A portable silane detector, if available, is an even better way to detect small silane leaks. At the sign of any detectable leak, you should stop work immediately and report the problem to your supervisor. Now that we have inspected and accepted the ISO module, let's follow the same team of silane operators as they connect and later disconnect an ISO module. One of the most important safety techniques when breaking into a silane process is the two-person buddy system. In this system, one person performs the work while the other provides a safety backup. The buddy system provides an extra set of eyes for early detection of trouble, and if problems do arise, having a buddy present greatly enhances your ability to control the situation, get help, and ensure the safety of everyone. After inspecting the ISO module and prior to performing any work, place a jack stand under the ISO module to provide secondary support to the chassis. Install an engineering solution to prevent accidental pull-away of a connected ISO module. Use a chain with a lock-in key, a glad hand lock, or a kingpin lock. If your process uses a key, place it in a secure location, such as on the module connection itself. Restrain or remove cabinet doors. And finally, be sure to install electrical grounding straps. First, open the pressure gauge isolation valve. At this point, the pressure gauge isolation valve will have about 60 psig of helium behind it. This might not register on the gauge due to the fact that the gauge goes up to at least
Hello? On? Are there any faculty members in the hall now? Any industry person in the hall now? No.
least 3,000 psig. If the pressure gauge registers above 100 psig, this could be an indication of a tube valve gross crossport leak. When breaking into a silane connection, always assume silane is present. Remove the disc caps while using nitrogen to purge the connection. If silane is present in this fitting, the nitrogen allows for the silane flame to be pushed away from the operator performing the work, allowing him to recap the fitting. Once the disc connection is opened, visually inspect the connection for any damage or powder, and replace the old gasket with a new metal gasket. Align the piping so the connections are parallel and not under stress. Torque the CGA connection closed to 35 foot-pounds or 47 Newton meters with a calibrated torque wrench, being responsive to the break of the wrench. Inert process gas panel and connection point, vacuuming up to the master outlet valve. Check for vacuum loss. If none is observed, brake with inert gas. If vacuum loss is detected, stop and notify REC Silicon. Remove the black vapor-tight cap from the Twintech Master Pneumatic Valve air connector. Ensure master air is off and all manifold valves are closed. Align notches, thread on Twintech connector, and hand tighten connection. Each numbered port corresponds to a numbered tube on the ISO module or master inlet-outlet valves. Apply air pressure, recommended at 100 psig, up to a maximum of 115 psig to the pneumatic system. Keep the tube valves closed and open master inlet and outlet valves and open all manifold line valves. Inert the manifold with helium to remove the oxygen to 25% of the LFL ratio, using pressure and vacuum up through both master inlet and outlet valves and the pressure gauge isolation valve. With the system purged, pressurize the manifold and connection piping to at least 1000 psig helium. The pressure gauge can be used as an indicator of pressure within the manifold. Leak check the module connections, both disc fittings, manifold piping connections, all fittings, and valve bonnets. The best method is to use a portable helium detector to conduct the leak test. Now vent the manifold. After venting is complete, close the master inlet valve, or the unused side of the manifold. Vacuum the manifold to 1 × 10⁻⁻1 torr up to the tube valves. To unlock the pneumatic tube valves, allowing them to open, turn the handwheel counterclockwise until you hear a click. This handwheel must be manually unlocked before use and locked before return shipment. To break the manifold with silane, close the manifold valves and then open the tube valves. Keep in mind that pneumatic valves are quick acting and will apply full tube pressure immediately to the system. Now use the manifold valve to introduce pressure between the ISO module and connected piping. Pressure swing the manifold and outlet connection piping with silane for quality purposes to remove residual helium, moisture, etc. Establish flow by opening all critical isolation valves on silane used system. Once silane has been introduced in the system, working in pairs is no longer required. But when it comes to handling silane, 2 heads are definitely better than 1. An ISO module like this can supply a manufacturing process for weeks, maybe even months. As silane is used up, the pressure will drop until it is too low to supply your process. Tubes should not be allowed to lose all pressure. Closely monitor tube pressure during operations, and as pressure approaches 50 to 75 psig, or 446 to 618 kilopascals, prepare to change out the ISO module. REC Silicon requires at least 50 psig for safe transport and to allow our factory technicians to sample the silane in the tubes. Returning a module to REC Silicon is a 2-part process. First, disconnecting the ISO module. Second, filling out a customer module return status document. The purpose of this document is threefold. First, it serves as a checklist of the steps to ensure the proper items are completed before the return of the ISO module. Second, it increases the safety of our operators. And lastly, it ensures that we are aware of any problems with the ISO module and can safely handle it upon its return. This generic schematic illustrates the main points of the disconnection process. Be sure to adjust your procedure for your specific process configuration. Unless your process draws down all tubes simultaneously, thus ensuring equal pressure between them, you must first equalize the pressure in the tubes. While still connected to your silane process, close the master inlet-outlet valve on the isomodule manifold. Then open the two tubes closest in pressure and let these equalize. Then open the next tube closest in pressure and continue this process until all tubes are equal in pressure. Next, close all the tube valves by closing and torquing the manual valves, or by removing the air pressure and depressing the actuator and turning the hand wheel clockwise on the pneumatic valves. Properly closing the valves in the ISO modules is critical to ensuring safe handling, use, and transportation of silane. The manual valves must always be tightened to the specified torque, according to the valve reference sheet located in the rear ISO module cabinet. A torque wrench is the only way to ensure a valve is correctly tightened and should always be used. If too little or too much torque is applied to a valve, it could allow silane to leak by and possibly result in a dangerous fire or expensive plant shutdown. Leaving the manifold valves in the open position, open the pneumatic master inlet-outlet valve, and then open the valves to your disposal system, which will relieve pressure from the manifold and transfer lines. When the manifold pressure is relieved, close the valve to the disposal system and retorque the manual tube valves. Pressure swing the manifold using nitrogen or helium. Remember to keep the pressure gauge isolation valve and the master inlet-outlet valve of the unused side of the connection open to ensure the entire manifold is inerted. Repeat the purging process several times to bring the silane concentration below 25% of LFL at a minimum. Once below 25% LFL, vacuum swing the manifold with nitrogen or helium. Then repressurize the manifold to about 50 psig, or 446 kilopascals with the inert gas, and close and torque all manifold valves, including the pressure gauge isolation valve. Also, remove air to both the master inlet and outlet valves. Vent the inert gas pressure in the pigtail connection and isolate the connection from the process lines. Now you can disconnect the manifold from the process lines. Remember to replace the gasket at the dis outlet connection with a new metal gasket before capping and torquing the connection to 35 foot-pounds. With the process lines disconnected, you may now prepare the ISO module for shipment back to REC Silicon. First, immobilize each manual valve by tying it with sturdy wire as shown. Next, make sure you've completely filled out your customer module return status document. Your company name, the number of the module, and the date go at the top. Then fill in the pressure and contents values for each tube, and record the torque value used on each manual tube valve, or indicate that the actuators are locked on the pneumatic tube valves. Next, report the manifold pressure and the inert gas used. Note the status of the manifold line valves and the master valves. Indicate that all manual valves were wire-tied. Record that new nickel gaskets were inserted and the inlet and outlet CGA caps were torqued shut, and the black cap was replaced on the Twin Tech. Record the car seal numbers from both the front and rear cabinets. Note any damage, as well as any additional comments you may have. Be sure to fill in your name when you've completed the document. With the paperwork completed, the module is now ready to be shipped back to REC Silicon. When we receive it, our technicians will go over it thoroughly, check on any problems you have reported, clean and repair it as needed, and finally, refill it for shipment. In the event of an emergency situation within your facility, the following response actions may be taken. These recommendations are not intended to supersede procedures and plans already in place within your facility. Prepare. Have a written plan of what to do for silane emergencies. This should include identifying the primary responders, preparing designated emergency equipment, and ways of venting or transfilling high-pressure silane. Identify. You should identify what warrants a response and call to REC Silicon. This includes 1. Brown or white powder visible anywhere on the ISO module. 2. Damage to the ISO module during transport that is severe enough to compromise its integrity. 3. Any detectable leak during incoming inspection or during use. 4. major fire in the facility that could impact the ISO module. 5. Manifold pressure that is elevated above the pressure indicated on the manifold tag upon receiving the module and opening the pressure gauge isolation valve. And 6. Anytime something is unclear or seems out of place when handling silane from the ISO module. If there is a fire, 1. Isolate the area for 330 feet or 100 meters. 2. Initiate emergency shutdown of the system. 3. Initiate E-Squad and or call the local primary responders if needed. 4. Do not extinguish a silane fire directly, but try to isolate or depressure piping or vessel. 5. For small fires, after isolating the fire, control its spreading to structures and equipment with dry chemical or CO2 fire extinguishers. And 6. For large fires, isolate the area for up to 1 mile or 1,600 meters or as much as possible. Cool containers with flooding quantities of water. Containers can explode or PRDs will relieve pressure at high temperatures. When cooling the containers, do not put water directly on leaks or allow water to freeze on leaks, as it may put out the fire and lead to an explosion. And always fight the fire and cool all vessels from a maximum distance using unmanned hose holders, deluge, and monitors. In the event of an emergency situation within your facility or during transport, contact REC Silicon's 24-hour emergency response line immediately. The response line is staffed with silane-trained individuals who can offer assistance 24 hours a day. If your facility is within the U.S., Chemtrek is available for contact during emergencies. We hope this video has been a useful guide to working with REC Silicon silane ISO modules. This video is to be used in conjunction with the silane training and operations manual and your company procedures. If there are any questions that have not been answered here, please refer to that manual or talk to your REC Silicon Gases representative. Thank you, and stay safe.
So you've got a good view of the, so is this audio on? Okay, great. So friends, you've got a good view of a commercial silane training, and as you can see, it is a highly specialized job. The technicians have a major responsibility, they are well paid, and these are the sort of jobs which will get created also when the fabs and this industry flowers out. So the purpose of this is not just to complete what we started yesterday on industrial safety. It's giving you a good view of the specializations that are involved, the sort of roles that could evolve, and let the dice roll and destiny decide what will actually come your way. Keep your options open is what I advised one of your colleagues earlier in the day, and pick up skills. Pick up skills left, right and center wherever you can, and don't say no to any of that. It really makes a lot of difference to your careers. I would now, just to summarize, we will be starting the actual sessions at 11 sharp. We have a time control with us. We'll start the sessions at 11 sharp. I have one more video which I want to play, that is on electric safety. How many of you were here yesterday and have seen it? Oh, most of you have seen it. Most of you have seen it. So I don't have to play it again. Then if you have seen it, and I can only say I'm sorry, the young lady is gone. She had the chalks. But I would have loved to ask you questions and check what you remember from that. Do you remember the energy which would be there at the limited restricted boundary of an arc flash boundary? Arc-Flux protection program. Anyone? It's 1.2 calories per centimeter square of area. How do you define that energy? It is defined by the fact that that is the energy which would create a second degree burn on an unprotected skin. Okay, painful but not fatal, easily addressable. Okay, does anybody know the symbol of a double insulated tool? Two squares, one inside another. That's right. So what's your name? Satish. When she comes, we'll get you your chalk. Okay. What is the current flow that can stop a person's heart? How much? 100 milliamp definitely will do it. Do you want to take another guess? Okay, the risk starts at 30 milliampere when the heart fibrillation take place. Okay, uncontrolled heart vibrations. Then it propagates at 60 milliampere, it can be fatal. At 60 milliampere, it can be fatal. 30 milliampere at 2 seconds exposure can be fatal. Okay, so those are just thoughts and notes for it. So how do qualified electrical workers ensure equipment remains de-energized while they are working on it? Prem, just, how do qualified electric workers ensure that equipment remains de-energized while they are working on it? LOTO. Who said that? Okay. What's your name? Yeah, he knows now. Okay. So, what's your name again, sir? Darshit. Darshit and, oh, he's gone. Okay. So, Darshit, thank you. You're right. It is LOTO, which stands for lockout tagout. It's a very important process. It doesn't just apply to electric hazards. It applies to all factory operations. If there is any possibility of a latent energy there, not just electricity, chemical energy. Okay, if you had noticed, I had yesterday shown that round plug. Okay, you might have seen in the commercial silent training, at one point they were having equipment with those round caps on the silent valve system. So primarily to lock it so that nobody can unlock it other than the authorized person. So it is they were controlling hazardous chemical energy. You can use it to control hazardous mechanical energy. Okay, so there are different types of lockout tagout components available with which you can actually do it. They do not cost much, but people are not aware of it. If you Google it, you will get companies which are giving those kits. They cost next to nothing, but they are life saving. You know, I think engineering is all about 2 or 3 simple things. Yes, there is a lot of design knowledge you need to have. There's a lot of technical skills you build up, but you also need to be very clear on being safe and having a good workmanship. If you can build that up in your entire execution, you are actually all set for an engineering career. Okay, I think I covered some of the questions which are there. Any inputs on earthing? How would you like to do an earthing in real life? take a ground wire and put it into the earth? Then what would you do? What are the steps? What would you do? 5? Pipe earthing is another way which people do it, but it is not the full solution. So really what happens in real earthing, the objective is, so I'll take example of, let's say, a solar installation. Solar installation at homes will have multiple earthing. First of all, the home wiring will have a separate earthing. Okay, the lightning arrestor will have a separate earthing. Okay, and the solar structure itself will have a third separate earthing. That's the ideal recommended earthing process. The earthing is done by taking the wire, taking a connection to ground. Okay, that is the literal thing. That connection to ground is done using ideally not a pipe but an electrode, a thick electrode pipe. That is the grounding electrode will be normally the best of them will be made of something like copper, or they will have a copper coating so that it can actually give you the lowest resistance to earth. The technical guidance is ideally you should get a resistance of not more than 1 ohm from your earthing resistance. So when you plug it in the earth, sometimes you do not get it. How do you make sure you get it? The typical contractor will just put charcoal mix in the ground and say, I have this will meet your requirement. But charcoal mix is also not adequate. The right process is to use an earthing chemical, typically bentonite, which you get in the market. You make a mix of it. Again, you will have good YouTube videos which can show you that. Basically, you mix that earthing chemical in the specified proportion with earth, water. You dig that hole, you put your electrode in it and surround it with that mix that you make on the site. Then you connect it with a wire to the structure. The wire that you use for that structure, a lot of times the contractor cuts cost by putting a very low, very thin wire on it. The normal housing wire is used for it. That is not right. Should use a thicker wire so that you hit that 1 ohm resistance guideline. Okay, you also need a thick wire because if there is any incidence, the current should flow to the ground. It should not flow through the structure at all. So these are the norms for it. So I'm just sharing some things from my life because I have seen some of these things actually being compromised and very critical. That's it. We are at 10:30. Officially, we break for tea right now. 10:30 to 11 is the tea break. We come back at 11 sharp. We will start. Okay. So my request is 11 sharp. Cheers. Grab the best seats. Since you are here, grab the best seats. I will just, you got a USB? Do you want to use, give me a USB? You want to use your laptop? Okay. You will connect after me? Okay, that will be the way we will do it. Tell me, tea service is on.
Yeah, he's just getting it.
Association of Semiconductor Manufacturing Industries, Society for Information Display is a global body for the display industry. Okay, and displays are very interesting components that go into your devices. They are the human machine interface, man-machine interface in real terms. They have moved excitingly over the last couple of decades. If you remember, we used to have the color tube. Okay, now it is no longer that. You moved on to LCD panels, and LCD panels have moved on to LED panels, and LED panels are again evolving. You have QLED, okay, where quantum dots are giving a life to the LCD panels with brighter screens, brighter emissions, and then you have other technologies which are shipping out. You have micro LED. Perhaps Prasad will talk about it shortly. Micro LEDs are raising the bar on the sort of resolution you can get from displays, more brightness. They are going to power the AR/VR headsets of the future. They are going to power your smartphone watch displays in future. So there are tremendous advances that are taking place in display, and it's also a very big industry worldwide. Society for Information Display is actually the anchor body, the flagship association, looking after the display industry interests in the world. So I had the good fortune, thanks to my role in applied materials, I had worked both with SID and SEMI, and today this part of the session I am actually leading as a consultant to SID. I want to actually share in the next few minutes a few quick messages on SID and why you should know about it. So SID is an international organization solely for display professionals. It's more professional oriented than company oriented. So a lot of people who are members of society are individuals, not just companies. Companies are a member also. They put a lot of their people, they depute for it, but SID is primarily focused on display industry, display professionals, and the senior most people out there, when I go to their flagship event in US, the display week has evenings dedicated to celebrating the technology achievements of this industry. The people involved there are people who are researchers, engineers, scientists who have worked in the display arena over the last several decades. You actually interact with people who have created products like the OLED screens that you have seen. You hear from them how they have created that particular technology, how it has moved, and it is absolutely exciting seeing their passion for that particular industry and how they are making these things move. If you go into a SID display week and their exhibition area, it is again mind-blowing. You see newer technologies on display coming in. When I have been to some of them where they will show you how the display will be flexible, it will roll and close, okay, and when you want to see it, it will rise out of the table or out of a rolled screen. You will see holograms. Okay, you're walking to a exhibition counter. This was Panasonic, and they had a hologram of an escort there. Somebody, someone who would be managing the stall. So that image would come up of a young lady who would be looking at you directly and welcome you to the stall, and you can be addressing her from whichever side. She would turn to you and look at you, and it's just an image. It's just an image which is actually reacting to your presence in that way. So a hologram, and again, that's the sort of work that's happening out of SID. So, so this is SID present across the country, a global membership, been involved with the development of the display technology sector blow by blow over the last several decades. There are cutting edge innovations that have shaped this particular market. they're involved with foldable displays. I've seen transparent displays, where the display itself comes on a transparent glass screen. There are flexible displays. You have screens which are having high refresh rates. The applications going not just to the conventional TV or just your laptop screen or your smartphones, going on to AR/VR applications, going to the fighter pilots' visors, where they would actually be seeing all the real-time inputs on their landscape. Crazy work, with a lot of the work actually coming also from people in their I zone, which is their startup zone, the innovation zone. So it's a fascinating association and a fascinating work being done by engineers out there. Applications are growing across different segments. Automotive is an interesting segment that they opened out. And again, when you go to automotive, you have moved from the time that you had those meters telling you what mileage it is. You're already seeing a lot of flow of LED displays in the cars. But imagine when you have almost a pillar-to-pillar display availability. So the entire front panel is having a conformal display on it, and you can actually see the data. You can see a lot of innovation on it. When I went to Dubai, some time back, my son-in-law was driving a car that had a heads-up display, and it was fascinating guiding him on the route, like we do on the Google map. But it was the car's front screen on which the heads-up display was projecting the route, and he was taking the directions on it. The Dubai technology implementation was so interesting. It was guiding when he was entering a zone where the speed was to be within a certain limit. And just imagine the level to which the man-machine interface is originating now. So very interesting. VR, AR is a reality. Holographs, ultra-thin displays. We are moving to a different world. CID is primarily aimed at building the display sector, networking. It has a very active focus on developing local universities and colleges to establish student membership. I have been with SID formally in this role only since September. I've already got 200 students who have come into the SID memberships in the last 2 months. Okay, I would like to invite all the students to take a look at joining SID. We'll send you the link on it. The cost of membership is very small for India at this point of time, especially kept by the SID membership at only $5. Okay, I want to show you what all you can get for that $5 separately. We will be conducting in-person workshops across the year. Okay, and I do hope to come back to Bangalore again with workshops like this. When I come with those workshops, SID workshops, they have actually made it free of cost for the students. Okay, so what is that $5? It's not even going to cover the cost of your meals. We would like you to actually look at it as our objective is to propagate the passion for display technologies in the country. One of the work which Applied Materials did do, and I through Applied Materials did do when I was with Applied Materials, was to propagate display technologies as a topic in the Ministry of Education. So now this is an approved course in the AICTE curriculums of 9th April. Okay, it is one of the electives you can take. There are 2 or 3 topics on that, on different display technologies, on the different materials that go into it. You can decide to take it as you wish. You can also decide, I'm not ready to take that as an elective, something else makes more sense for me. You can do that. But important thing is, it is an elective. Important thing is that in the new education policy, you can keep on adding skills and certifications. Do not stop on it. Do not stop on picking up your skills and certifications as you go ahead. I myself have not stopped. I will have over 30 certifications that I have built up over the last few years. And that's just the last few years. Okay, don't stop on that. Pick up the certifications. It's a great high. And nobody says that you have to be a government affairs guy just because you're not, you can't be a technical guy just because you're a government affairs guy. So pick it up. Okay, I'll show you the sort of content in a few minutes, but they have a lot of relevant stuff, and you should actually engage back on that. Is Darshit here back? Darshit is not back as yet? The guy who responded with the answer? Who are the people who responded with the answer? You did. Did you? You did not. Okay, there was someone here, there was someone there. So, I covered that. I'll not repeat that, but there are a lot of benefits of joining in. A, you will get to network, get an access to the technical content, and some of this technical content is mind-blowing. It can cost you about $1,000 for a single workshop abroad, and you actually get it free of cost. One course from the rich library that CID has. They have permitted you to take one course free of cost when you take the when you take the student chapter membership, and you get the journals which give you updated on the information. It will be a soft journal, but it will give you a very good idea of what is happening. If you're planning to continue into engineering, you'll get a lot of interesting prior work references which will help guide you on what you need to do. At Manav Rachna, we had one interesting person. His project was integrate the application to AR VR to actually guide differently enabled person on how to navigate in a real life situation. So the possibilities are so immense. These are things we would not have been thinking of in our engineering days, all that 40 years back, though I'm not that old. But I can tell you, the young generation can really take off from some of the tools now. So key takeaways, with CID, you're getting very interesting, rich content. You will find a rich resource for Indian academic institutions. There are unique CID certification programs that it is worth adding to your portfolio of certifications. There will be a lot of Indian webinars and in-person seminars. Leverage it. That's the key message here. Before I hand over to my industry colleagues for taking this ahead, I want you to get a quick feel of the site. This is the CID.org site. Okay, just type sid.org and you can get into it. I am a member, so I can log in. There you are, I'm logged in. These are the journals. Okay, and if you actually go into the CID.org part, I want you to take a look at the content. These are the webinars. Okay, and these are still not the courses. Courses are separate. Courses are separate. You can see it from the side. But take a look at it, the topics that are there. The headset-free virtual monitors, the enabled AI glass through single panel RGB macro LED, the role of perceptual imaging in AR, VR, XR, the role of man-machine interfaces, because that's what it is. How much of display do you really need in a car, okay, before it starts becoming an overhead on the individual? The studies on that, cockpit designs, the automotive cockpit designs for the future of mobility. There are such interesting topics, and it tells you it's not just, engineering is not just about doing the basic device physics. It can be about designing that specific environment in which that technology is going to go. How to make it palatable for humans. There is so much of work being done on it, so creatively, so intelligently, it's mind-blowing. So at this stage, my key message to you is, do take a look at SID as one of the things that you should join. Send you more details on it, but let me invite at this point of time my guest speaker today, Prasad Madhavotla, Group Head for the Display Engineering Business at Applied Materials. Prasad, your session, your audience.
Good morning all. Hope you all can hear me, see me. Okay, so I'm Prasad, Prasad Madhavapla from Applied Materials, and I would like to take you to what is display and how display has become an integral part of our life day to day. Yeah. I think we have students, academia, and as well as industry. All our day starts with, we just say like this, and then once we go to bed, and also at the time also we do the same thing. So display has become so much into our life, right? And if you see this conference, first of all, I would like to thank CeNSE IISc and IISc giving this wonderful opportunity to interact with the students as well as the other industry partners and my old friends whom I see in pretty much all of the display conferences and all. So thank you for that. And coming to this particular conference, yesterday you all discussed about what is the semiconductor manufacturing stuff and all. So those are all the things which we really don't see. That is pretty much everything is inside. And now display is something which is outside and you can see and feel. So let me take you through what we can see and all. And as I said, I'm from Applied Materials, and whatever you see in this particular slide and the presentation, it is more on the forward-looking stuff and all, so which we use it. And Applied Materials is number one in terms of the semiconductor and display equipment. We are into the precision materials engineering. So be it a semiconductor or display, it is all the material deposition, whether it is chemical vapor deposition or a physical vapor deposition or evaporation, etching, all these functions are pretty much there in semi as well as in the display. And Applied Materials which makes the equipment which can do all these functions in any display or a semi fab. And as I said, so we are into the technological innovative company, and if you see the number of patents and everything, so that itself gives a kind of a proof point that how we are into more in-depth into the precision materials engineering stuff and all. And Applied Materials into semi as well as display, and also it has the services industry also, which caters the needs of both semi as well as the display. And coming to the display, right, and Applied revenue stuff and all, more Applied is focused on the semi side, and also you see that everywhere, if you go to a semicon or anything, it's more onto the semi side, and we are making more efforts on putting it, how we get, we give the awareness onto the display side to the industry, academia and all. And coming to here, right, so if you see in this particular slide, so this is a semiconductor equipment where it is pretty small, and you see a 200 mm wafer or a 300 mm wafer, so doing all this materials engineering on it. And below what you see is here, it's a display equipment. This equipment is so big, and you have more space to do the maintenance stuff and all. So here people really struggle how to do the maintenance stuff and all, and here at the downside, right, you have enough space. But the technology side, what the process which is happening here, here it is having the PVD process, and below also it is having the PVD process. The process is same, and the difference is there the process is done on a wafer, and below you see process is done on a glass substrate. Yeah. Any guesses in display? What is the thickness of the glass which people use? Maybe in a mobile phone or a TV or anything. Any guesses? Thickness of the glass. Anyway, chocolate will be given by Ashwini. Yeah, I'm not carrying that. Yeah. No. The present running thickness is 0.5 mm. So much thin glass which is used for a display panel. And so if you see the technology stuff and all, just imagine, right, we don't have this flat panel display, right, and we are still in the CRT era. Can you just imagine your phone, how it is, or your TV, right? It's becomes so big box, and if you just see, okay, whatever the screen, if you want to make a digital stuff, just imagine a CRT of a screen. Yeah. So the thing is, the way the semi growth is going, in similar fashion the display has to go. That is only the reason. So you see your smartphone, smartwatch, or a TV and everything. So it has become possible. So that means we came from the CRT era to the LCD era. It is a very big inflection. That is because of the technological innovations which have happened in this display area. Right? And this is also very much important in the semi side, how much speed you go, how much speed processor which you have, but just imagine your mobile phone without a LCD display. Coming to that, so if you see, right, from CRT to the LCD, it is a big inflection, as I said, but it took so much time to become a something like a consumer product stuff and all, because earlier the LCD started with some kind of with the laptops and some lab equipment, lab laptops and all, but now the LCD is everywhere, right? Anyone who is not having a smartphone here? No. Right. Everyone, right? I think it is that much penetrated into this particular thing. But now the things are changing, the requirements are changing. LCD, yes, it gives a better picture and everything and all, but we are now moving from LCD to OLED. In the mobile side, we already moved, and whatever you see in your mobiles, right, is you see AM OLED, active matrix organic light emitting diode display, right? So it is already moving to OLED. But what is the advantage which you see with OLED? Okay, brightness. Okay, what else? Resolution. Okay, resolution, pixel. Yeah, it is. Okay. In devices. Okay. Okay. And one more additional advantage which I can put is OLED is more flexible. Because of OLED, you can see your curved displays, your camouflage kind of displays, that means foldable phones. Even now in future you will see a rollable displays, that means you can just roll it, which is already possible with OLED. So that is one of the inherent advantage which this OLED is having. So this is the OLED era, so where it started with mobile and now it is moving on to the TVs and then the IT side also, this OLED, because of this advantage. And as Ashwini has mentioned, right, I think the next era is to go with the micro LEDs. So that is another new technology, but when it comes in 2030, that means in the next decade only we can see that. And the future, what we see is a natural 3D stuff. So that's where the industry is working on now, because we are all with the 2D devices and everything, but what next we need to go, it is a natural 3D. And then more AR, VR stuff and all, right? AR, VR, I think it is more look and feel stuff and all, you can really feel it. When you wear a VR headset, you are in a different world, right? So these are all the things, okay, which are happening due to the technological inflections which are happening in the display industry. Coming to what are the things which are driving this? In display, if you see, there are mainly three things which will drive the entire industry. So one is the size, right? So you always look, okay, 5-inch mobile or 6-inch or 6.5, like that. When it comes to the TV, again, right, it started with 22-inch and now, yeah, 40, 43 has become a standard for every one of us, right? So the size, that is very much important here. And there is a transition which will happen from LCD to OLED, and here I put this one. So anyone can guess what is W OLED? White OLED. So it is really not a real OLED, it is a white OLED with a color filter which is added to it, so that you can really see a good viewing angle and other things. And QD, I think you already know it, most of you, quantum dots. But the real OLED comes, that is, we call it as a RGB OLED. That means you have the red, blue, green, all three organic depositions happen for each and every pixel. So that is the real OLED. And what you see on your mobiles is the real OLED. And so that is the size. And the next thing is the resolution stuff and all. Resolution, so if you see, right, the resolution which you see in TV and resolution what you see in AR, VR headset is entirely different. Any guess what is the resolution of a VR headset? No. Yeah, it's okay, we call it as a, okay, K and PPI, so both are different. So okay, maybe I can give you one example. So whatever the phones which you use, the resolution is around 400 PPI kind of a stuff, pixels per inch. So that is what we call in the resolution side. And whatever the TV which you use, it is 80 PPI, something little bit more than that it goes on. But AR, VR, the resolution should be more and more, then only you can have the look and feel. So if you want to have a good look and feel, you need to have minimum 1000 PPI, 1000 pixels per inch you need to have. And now the running is 1500 and 2500. So if you want to have a better VR headset with a better resolution stuff. And yeah, it is not yet commercialized. Yeah, so now the thing is going on with 2500 is the one which we see. Yeah, thank you. And the refresh rate is another big thing, right? And so when you use the OLED, okay, one more question. If you want to make a display panel, how many glasses you need to make it? Yeah, you need to have two. One we call it as a backplane, and one we call it as a front plane. Backplane is mainly the transistor and all this electron mobility and everything happens, and the front plane is for the color and other things. Right? So these are the two things yeah, which we see. And as I said here, okay, this is also giving a hint. So transistor, it is for the backplane, and for the display, it is for the front plane. And the transistor, the technology changes from the amorphous silicon. So this is the technology which is used in the TVs. But if you see in your mobiles and all, the change is pretty drastically it is happening because of the higher electron mobility. So that is very much important, particularly in your mobiles. If you need to have the refresh rate and then electron, because when you do the touch and then if you scroll your screen further and all, right, it has to refresh pretty fast, and the electron mobility has to become so fast. So that is the reason. So this polysilicon, low temperature polysilicon, and then the oxide displays are making it to happen. But if you want to know more, yeah, I think as Ashwini mentioned, right, you need to go through this SID stuff, and then it is having much more technical content into it. And coming to the display, right, and the LCD, right, that is already everyone knows it, but from LCD to OLED it is happening, right, because the OLED, so if you see, it can be a white OLED or RGB OLED, this is happening. And one more thing is the rigid to the flexible, right? So whatever the glass which we see, right, it is pretty much the rigid displays. Now we are working on more onto the flexible display stuff and how to make it more rollable, bendable kind of a display. And then the next one is 2D to 3D. So these are the main factors which drive the technological innovations in the display industry. And okay, whatever the technology, right, if there is no customer to buy, then it's of no use, right? So that's why we say, okay, innovation and commercialization. So these two have to go one end to end. You invent so much fantastic stuff, if no one is buying that, it's of no use. So in display industry, it is pretty much a different kind of an industry where the initial cost, even, right, just imagine, right, if you go through the 15 years or 20 years back, the LCD TV cost, and now what is the cost of an LCD TV? There is a huge drastic difference, and then it gone down so much, right? So that why there are three drivers which are making it to happen. One is in the initial size, okay, so when you start the LCD, we start with a smaller generation glass. That means the glass substrate is 1.5 meter by 1.8 meter kind of a glass. Of course, thickness is 0.5 or 0.7 that inch. So, but how many displays you can make with that glass? Very less, right? But how you can bring down the cost? That means you have to take a very bigger glass. So say, okay, 2.2 meter by 2.8 meter, that we call it as a generation 8 glass. Then you can make much more displays with that. Then the cost of per unit will come down further. And if you want to further bring this down, you have to go with 3 meter by 3 meter kind of a stuff. Then you can make more displays with a bigger glass, right? So that is how the cost is coming down from generation to the generation. One more. So in the industry, so what is the biggest glass which we use in terms of size in display industry? Any guesses? I already gave some numbers. Yeah, that's okay. We passed that. Yeah, we passed that 3 meter by 3 meter in 2007. No, we are still in the 3 only. Yeah, it's 3.8 meter by 3. Okay, up to 4 meter. Yeah, 3.9 something. Okay, which we are using it. That is the biggest glass. We call it as a generation 11 glass, which is, just imagine, right, that much big glass, this much thin, 0.5, how to handle that, and how to do all this deposition stuff and all. So that's where the technology comes into the picture, right? So Applied Materials and of course even we have our competition, so they are also working on so much onto the technological innovation to see that how to make this a bigger glass, and then with lesser time do the deposition, so that we can bring down the cost further and down. And the LCD, if you see the scenario, right, so now in 2020, so when it started, $30K USD to $100, so that much drastic change, but it took many years, and now time is so much, right? I think we can't wait that much, right, because we want fast, okay, the latest technology at lesser price at a faster rate. So now, so if you see the OLED which has come into the picture now, it started pretty much in 2000, because even though the OLED technology evolved even before that itself, but when it comes to the commercialization of this, it took a bit more time, right? But for the OLED to comes down, right, I think 2025. So I think maybe after that we can pretty much see a drastic reduction in the OLED panel stuff. Okay, if you want to wait, yeah, you can wait to buy a new TV or OLED TV stuff and all. Okay, so here the thing is, even Applied pretty much into it, and we recently, just 2 weeks back, we announced our new product called Max OLED. So that does all the OLED evaporation stuff with all these RGB pixels and everything. So that is a new technology which we have, and pretty much our Samsung, so which is evaluating this particular new technology, and we'll be shipping one tool to them soon. Yeah. What after OLED? So micro LED, but is it really good to buy now anything on this? It's so costly, right? Even I don't want to afford to buy that. Yeah, but after 2030, we can pretty much see a micro LED stuff and all. Till that time, this OLED will rule the world. Yeah. And also in between something has come, right? Mini LED and backlit LCD. We all call, okay, LED TV, LED, but it is not a LED. It is a LCD TV, and on the back light, it is made up of LEDs. There is no backlight stuff, but LED itself acts as a backlight. That people call it as a LED TV stuff and all. Okay, what Applied Materials is doing in this? So, be it a LCD technology or a OLED technology, we have our equipment, right? And as I said, there are two glasses, one front plane and one back plane, and in between you have this liquid crystal stuff which we use, and then a backlight. So this is a simple way of showing a display module stuff. And this chemical vapor deposition, physical vapor deposition, and the color filter, all these things are pretty much used in the back plane processing as well as the front plane processing stuff. Coming to OLED, things have changed. So do you see here any backlight? No. But you still see this TFT, right? No backlight, but you see the TFT. But the TFT technology is changed. So for the higher refresh rate stuff and also, you need to either have the LTPS, LTPO, or the metal oxide stuff, so that you can have the higher refresh rate. And if you see here, right, this front plane, it has become a RGB OLED emitter. That means you really no need to use another color filter stuff and all, so you can use it. But there is one additional stuff which we are using it here, that is thin film encapsulation stuff. So OLEDs, the disadvantage is when it is exposed to oxygen, it dies. So we need to encapsulate this OLED layers with a thin film encapsulation stuff, so that we can give more life to this particular OLEDs. And micro LED, so that is the new one, even, right? So with the micro LED, right, even the other thing, here you only 3 you have, and here only 2, right? That means things are even becoming more and more easy, right, with the less processor stuff and all. So here you have this RGB micro LED chips and then TFT backplane. So that you can pretty much see how the technology things are happening. Coming to a little bit on the Applied Materials India. So we are more than 8,000 people working for semi as well as the display side, and we have our presence in Bangalore, Chennai. Means wherever you see a IIT, and so you see that, okay, we have our presence. And also recently we have expanded in Coimbatore and Pune to take the new technology stuff and all. Yeah, this is okay. Our Bangalore campus is an ITPL. Sorry, pretty far, and if you are residing here nearby, then I think you need at least 2 hours or 3 hours in this Bangalore traffic. Yeah. And we have a pretty good exploration lab and a Quest lab, digital lab, where we do the actual process and everything and all. And this is what is helping us in driving to the next level innovation stuff in future. Yeah. So ultimately, right, so what I can say is that so we are, okay, without our customers, we cannot do much. So we always partner with the customers, because customers will tell what they want. Then we do the inventions on that particular technology and on that particular process, right, so that we can move forward. For example, right, have you heard of plasma TV? Yes. Now do you see any plasma TV? No. So that means the invention and innovation happened, but the commercialization didn't happen there. So any industry want to work on that which has no commercialization? No, right? Or you want to work? No, right? I think so. We want basically, right, commercialize the stuff and all. So always we need to know that, okay, what our customers want and what is the latest technology which is a game changer technology for the future. And Applied Materials works on that. And our effort is to make this the displays new. Coming to India chapter, right? India, so dream is to, okay, have a display fab here. So we have been working, even Ashwini is there, I think when he was working with Applied Materials, I think in 2017, from there I think our journey started. But still, right, we have not seen a display fab, but there is a lot of work which is going on from the LCNA side and others, SID, working on to give more awareness on this, the display, so that one day we will see a display fab here. So, and we see that, okay, there is a great opportunity for that. And coming to that, so the consumption, India, if you see, if we make the displays for the Indian consumption itself, that's a very huge market. Right? So there is a good market. So for us to, okay, if we have a display fab stuff and all, so that is another thing. And then, so we want to see that, okay, how, which technology and which fab we need to use, because this display technology has already evolved, and that means there are people, means our customers, they already know, okay, which technology is going better. That means we really don't make any mistake, right? Because already few people made mistake and then they learned, and then we already know those learnings. That means we know where to start, right? Which size of fab we need to have it, which technology to have it, so that we can be more competitive and commercially successful and all. So India has that kind of unique advantage, and we hope this particular technology will come soon. And this is my final slide. So we want to make okay, better future, but at the same time we want to make a brighter future with the display. Yeah. Thank you. Yeah. Yeah. Maybe I need to check with the Ashwini, because I took a little bit more time. Yeah. Okay. Yeah. Unfortunately, I don't have a slide, but I can take you through.
One of our future speakers, Dr. Steve, will be covering something. Okay.
So okay, that's good. So basically, like, you need to go with TFT backplane. So that is a big process which is there with the lithography, with chemical vaporization, physical vapor deposition, everything. And after that, front plane, there is a different process which happens and all. So after that, both we merge and then seal it, align it, and then put the liquid crystal inside, so that you can become a display. No. It is the TFT backplane. It is the glass. That's where it's no silicon. So it is the glass substrate on which all these processes and everything happens.
Panel manufacturers currently.
Okay. Panel means, okay, we come up with Corning. Corning has a pretty good panel manufacturing. Even our customers take most of the panels from Corning. Glass.
Just the glass.
Glass substrate stuff and all. Yeah. I think your question is that, I believe, right? Okay. Yeah. Only the glass substrate. Panel means again like Samsung or our customers, they make the display module and display entire panel stuff. No, I think there is a one company, okay, Indian company, what is that, Vedanta Group. They acquired one company called Avanstrat, so which is a panel manufacturing thing, but the facility is not there in India, but they get the panels and do all the transportation and everything from here. But at present, no. But you said right, I think so. If we need to start the display fab here, first we need to have the panel manufacturing.
If I may ask, what kind of like what generation fabs they wanted to establish in India, like LCD or OLED?
Good question. So here, when it comes to the fab, you have to see, do you want to cater to the needs of the mobile business or a TV business? So both are separate. So if you want to go with the TV, then at present, if you see the industry body and the ministry and all, they are looking into the Gen 8 and Gen 8.5 fabs for the TV. But when it comes to the mobile, then you need to go with either Gen 6 or Gen 6 half cut fabs, because where the consumption is not much and you really don't need that much bigger panel.
And there were plans to go into OLED or LCD only?
again, right, I think so where to start, it is a big question still, right, whether to go with directly with OLED or shall we go with the LCD and then to move to OLED. So it's still a question, yeah. But for the TVs, yeah, it is pretty much LCDs, yeah.
Okay, one question about applied materials. In India facility, you are supplying the like the equipments for panel manufacturing, like.
Okay. In India, so we do the design and engineering and reliability stuff and all, but our manufacturing facility is there in Taiwan.
Okay.
So the equipment is manufactured in Taiwan.
So here there is design of the equipment.
Design, engineering, reliability, and also we do all the testing and everything, but we don't manufacture.
Thank you.
Yeah.
So is there any linked incentives like PLI, anything government is offering for the fab?
Maybe I think you are asking wrong. Maybe.
What is the question? What is the question?
So government is giving any incentives for setting up the fab in India right now?
Of course they are.
Yeah.
Okay. The display fab is one of the approved categories for which the government is giving 50% from the central government. The states are giving anything between 20 to 25% of the project. So a display fab project can really get subsidized almost in the ratio of 3 to 1. Okay, even if they give 20%, there are other subtle benefits. Land is being given at a throwaway cost for the project. There are benefits given on supply chain. There are cost of power and some of the inputs is subsidized very, very attractively. So I think I don't think that money is, the support from the government is not an issue. The new ISM funding will be announced by February end. Possibly earlier in the budget, we'll get to know of it. That's going to be a huge tranche of money. The previous funding was about 1.5 lakh crores. Okay, that money is already committed out. The new money which is going to come in will go into allied fabs, which could be compound semiconductor fabs. It could still permit for a major fab project, okay, for semiconductors. It will definitely permit a display fab project. You know, it will also permit for the, it will also focus extensively this time round on the supply chain. So money will be given to the supply chain of the display and semiconductor industries to come to India. That's a real opportunity. Like I said, don't get constrained in the thinking that only a fab is the final job role or opportunity. Be flexible. The skills that you're going to pick up are going to flow into a lot of industries, a lot of companies, and you will get you know, a good you know, good opportunities should come up in the next few years. My one recommendation back, so are you ready? Come. So my one recommendation back is keep on picking up the skills. Just keep on picking up the skills. I want to add, Vedanta is no longer looking at a fab, display fab project. There are global companies looking at India. Depending on how the project focus is announced in February by the government, the fortunes of the display fab will be unveiling out. Irrespective of it, display assembly has already come into India. Okay, so while they are not creating a glass with all the circuitry on it, they are looking at getting the backplane into the country, and they are looking at assembling the final product out here. That started. Some elements of the supply chain have started, which is all a harbinger of you know, things to come. Okay, if we get one good display fab project, the industry is set. Whether that will happen or not, time will tell. Of course. Yeah, of course. So you are. Oh yes, one important thing. Prasad.
Thank you.
Thank you, Prasad.
Thank you. Thank you for the opportunity.
Really appreciate it. Yes. So let me introduce Dr. Gurumurthy Hegde. He is our next speaker. He's a member of SID. He is a professor of chemistry and a passionate researcher in the display area. He's going to present on display materials today, but he will also give a contextual input to the display industry. On to you.
Good afternoon, Ashwini. First of all, let's thank Elsina and Dr. Ashwini Agarwal for inviting, and also Ratna is here after a long time I met. And I think Mr. Prasad made my job easier because I wanted to present some slides. I can skip now because he already told many things which I'm going to present. I mostly give a slight introduction about LCD, LED, OLED, QLED and all. Then I will touch upon LCDs because that's where, as rightly pointed out, we have to start with LCD because directly we cannot jump into the OLED. Without father and mother, we cannot directly identify the kids. We should have some base because for a country like India, we have to start with the LCD first. Then I think we have to move forward. That's, I think, a good way for us to go forward. So size really matters in the world, you know. So in earlier days, if you want to carry all these books with you, it's a bulky size. You can carry 5 books, 6 books, 10 books, depending on how good you are at your gym, how good you are at your body. It's depending on you, you have to carry all these things. But the thing has changed when display has discovered the several of these books has put into the one laptop. The future is several of laptops can be put into the flexible displays. So that means size really matters. When material becomes smaller and smaller, you can able to see what kind of effect it will bring, whether you apply the electric field to the material, whether you can apply the optical field to the material, magnetic field to the material. Whenever you apply any field to the smaller material, impact is higher. That's why the famous statement from the Richard Feynman, there is a plenty of room at the bottom. So whenever material becomes smaller, we can tune the material the way we want. Having said that, you can see that in 1980s, if you are sitting in front of your table, you have all kinds of gadgets, whether you take your books, whether you want a calendar, whether you want the photos, whether you want the fax machine, newspaper, whatever you say, you don't have any space to write your notes. And thanks to the display, ever since display discovered, you can see that whatever the gadgets which I am naming here, which went inside the displays, right? It all happened within the short span of 30-35 years. So 1990s, where liquid crystal display came to the market, and within 30-35 years, it revolutionized. You, especially in the pandemic, you imagine if there is no displays, how we have to spend these pandemic years. Even the entire education system, it needs to be collapsed because we are not meeting it all. So that's the power of display industries. So it changed all of us. Now India, few years ago, everybody told that India cannot adopt digital payment system. But India is the best in the world to adopt the digital. Even vegetable seller is having digital payment system, all because of displays. Without display, we can't imagine how we can spend. Having said that, in 1980s, if you want to carry all these gadgets with you, it's estimated that you have to carry 250 kilograms of luggage every day, whether we want all these gadgets with you. Today, your 250 grams of mobile is carrying. We never imagined within such a short time, 250 kg of luggage we are carrying every day. Again, thanks to the display industries. Because of them, we are having a better life now. It's a very famous statement, people do not buy the technology, they buy the product. When we go to the market, we are not asking we want Samsung technology. We don't ask we want the Apple technology to buy, but we are asking Samsung products, Apple products to buy. So if you make a product for the poor people, anyway rich will buy. So that's why, how to make this product available for the poor people? It's possible only when material becomes small. So when material becomes smaller and smaller, we can able to reduce the cost. And again, people should purchase more. As Mr. Prasad rightly pointed out that as the buyers increases, we can able to reduce the cost of the devices. So country like India, we have our own market. It's a huge market for us. If everyone starts buying, we can able to reduce the cost of the device. Again, we can able to bring the innovation to these things. There's a lot of opportunities for us because a lot of new innovations, lot of new materials can bring changes to us. So when I am talking about innovation, where we are standing, you can see this is the recent data about global innovation index. India is 36.6, which is, we are much better than many European countries. We are much better than some of these countries, and we are very close to we are better than the Russia in innovation. But it is just a beginning for us. It's a long way to go for India. So whereas many countries have saturated innovation, but we are just starting. You just imagine next 4 to 5 years, our innovation index will go like anything. Again, we have a lot of opportunities because there is a lot of students here. We have a lot of opportunities in this area. In display, semiconductor is coming to India, then display should come. Then there is a lot of job opportunities. Not only in display, there is a materials, not only for scientists, engineers, even sociology, psychology, finance, all branches will get the job because everyone is required for these kind of industries. Then again, this is another important thing when you are doing this kind of display industry, whether we are satisfying the SDG goals, where exactly we are falling in this category. You can see one is industry innovation and infrastructure, second one is the quality education. These are the two important sectors we have to take care when we are talking about such kind of display industries, because first thing is we have to create the manpower. That's because we don't have dedicated courses for display industries. Only recently we are starting few courses on display industries. So there is a lot of such kind of courses should appear, and a lot of manufacturing technologies, lot of trainings, lot of seminars is required. That's why thanks to the Society for Information Display, which is helping us to conduct such kind of courses, lot of display related courses is going on. What kind of market we are talking about? This is the display market size 2023 to 2034. You can see 2034 it is estimated 377 billion US dollar. That's the market they are predicted by the President's research. That's a huge market. That's again every year it is growing. If you see here, it is at 2024 it's 182 billion. It's almost double than that. So it's a huge market ahead for these things. Then again, this kind of the battle of display technologies, what kind of thing we have to think when we are bringing these technologies to our country. First thing is the basics, display basics. That's why the AICTE has introduced these display technologies like quantum dots, then nanomaterials, then liquid crystal displays, LEDs, QLEDs and all. The next is we have to take care of the viewing angles, how big we have to make when we are making big size, whether it can able to give the better viewing angle for us or not. Image quality, which is extremely important when you are talking about display industries. Cost consideration. For a country like India, we cannot make a extremely expensive displays. We have to make sure that our people should buy those kind of technologies. So cost is the extremely important factor, which already Mr. Prasad told earlier. Whatever the technology we do, whatever the innovation we do, if it is not affordable, there's no use for that. So we have to make sure that it should be reasonable cost to buy for that. Power efficiency, which is again important because we have to save the power. Environmental impacts, again we are all going with a net zero, then carbon, this one we have to reduce the carbon dioxide. All these things factors come into the pictures when you are starting such kind of technologies. Durability is a very important parameter. Then specialized applications, what kind of application we can think of when you have such kind of display fab setup comes here. As of now, you can see the picture quality wise, OLED is better because OLED is having excellent picture quality. Power consumption is very good in OLEDs. When it comes to the LCD, lifespan is very good. Price is affordable because anybody. So if you are not worried about the price, then you can go with the OLEDs. If you are worried about the price, you can go with the LCD. So it's depending on consumer as of now, which one you are going for, whether you want to go for LCDs or whether you are going for the OLEDs at the time being. But as year passes, when more and more people start buying such kind of TVs, then again both LCD is already its affordable price, then OLED price will also decreases. So it's up to the customer to decide all these things. So this is a PPI PLA, which is a pixel per inch per length angle. Whenever we are talking about display technology, it is the determinant factor for image quality. So how much PPI PLA these kind of technology is present? You can see LCD is always having lower PPI PLA. So because of that, this is not, sharpness is not that much great compared to other technologies. and again it's a less clear compared to the others. And but the most important quality of LCDs, it's affordable. It's not so expensive compared to other technologies. Whereas when you come to the LEDs, it's having higher PPI, PLA compared to the LCD. I'm not telling other thing. Compared to the LCD, it is having higher PPI level. Then again, because of PPI, PLA is little bit higher, it's a sharp and clear images you will get, and also used for high-end monitors. OLED, which is higher PPI, PLA as compared with LCD and LED. Because of that, you will get very sharp images and clear images, and are used for high-end smartphones. Not only smartphone, you can use it for everything. This is the major thing I am talking about. In terms of the share, the major share is on smartphones. The next is the future is the virtual reality, where it requires the very higher PPI, PLA compared to all these three, and because of that you need, because whenever you are talking about virtual reality, you need a very sharp and clear images for that, and no eye strain because of these parameters. So materials, what kind of materials required? You can see the LCD, as the name suggests, it requires liquid crystal. Again, when I am talking about liquid crystal, how to fill the liquid crystal, what kind of glasses required, what kind of technology is required to fill the liquid crystal, seal the liquid crystal, then what kind of UV curing material is required. So material plays dominant role in all these technologies. Again, backlights, color filters, glass sheets, polarized glass shields, and thickness, all these things matters. When we are talking about LEDs, it is mainly about semiconductor compounds like gallium arsenide and gallium nitride, silicon, aluminum, printed circuit material, seals and gaskets, specialty lubricants, so many materials required. Why I am showing this is there is a lot of opportunities, none of these available with us. We have to start everything from the scratch, only few things available, everything we have to start. There is a lot of opportunity for youngsters to pitch in and to make a startup companies, or to learn these techniques, or to take the training and start their own business. When I am talking about OLED, there is again substrates, then anodes, then hole injection layers, hole transport layer, electron transport layer, hole blocking layer, electron blocking layer, all these things are required. So a lot of things required when we are talking about material side. And QLEDs, again semiconductors, nanocrystals, LED blacklight, liquid crystal layers, quantum dot filters, ZNO nanoparticle, which is required for synthesizing the quantum dots, graphitic C3N4 quantum dots, all these things are required because it's new technologies. Again, I'm just rushed through because of the time. So when we're talking about LCD OLEDs, obviously OLED is better because of the high contrast, vibrant colors and deep blacks, and OLED displays do not require a backlight because each pixel itself emits the light. You have seen the AMOLED displays, but out of these AMOLED displays having more power, although it's a better contrast, whereas LCD displays do not suffer from this kind of burn-in or power because it consumes a less power and cost effectiveness, and OLED displays are susceptible to burn-in issues. So there is always pros and cons in both technologies. When you compare AMOLED with respect to LCD, a variation of OLED, this one, offer faster response times, higher refresh rates, and compared to LCDs, ideal for gaming because that's where you need a very fast response time because molecules should move as fast as possible. Again for the virtual reality, but again consume more power compared to the LCDs. When you compare LCD with the e-ink, electronic ink, commonly found in electronic readers, it's great, but problem is it's not color. It's a black and white, and even in the direct sunlight and consumes minimal power here, but the lack of color production. Because of that, again you have to go to the LCD for color rated images, but it is having its own advantages because many people want only black and white when you are reading the e-ink, so they don't want color for that, especially for the e-books and all. So micro LED, already Mr. Prasad already told, micro LED displays are considered the future of display technologies. There's a lot of research going on. It's the benefits of OLED it is giving, but without the burn-in issues, which is the big issues for the OLEDs. Utilize microscopic LEDs to create the images and is still in its early stages, so a lot of improvement needs to be done on this sector. So another interesting technology which is called as LCDX, which is liquid crystal diode extreme, which is again new technology. This technology gives high resolution and a pixel density. It's a liquid crystal diode extreme technologies, low latency and high refresh rates, What's the latency? I already given the definition there. So wide color gamut and high contrast ratio, low power consumption and locked side fan. Again, we have to see how good technology will get in through, so that you can reduce the cost of the devices in coming days. So again, PPI already we discussed, I don't have to do much, it's already pixels, you can see here pros and cons. I have given the pros and cons for all these technologies. The LCD's pros is more affordable and energy efficient, then cons is lower PPI compared to the other display, whereas AMOLED is having the better contrast and more expensive LCD displays. Then OLEDs, best contrast and color accuracy, but cons is most expensive display technologies, and Retina display again offer the highest PPI and the sharpest images, and again Retina display you can see the definition because Apple introduced this Retina display concept. So next, basic LCD structure, as already pointed, it's a very simple LCDs where you need only two glasses and two polarizers. The one is the top, which is called as a polarizer, another is the bottom, it's called as an analyzer. And again, as earlier speaker told, the bottom one comes with all the other pixels, everything is attached to that. So this is a polarizer and analyzer. Then there is a spacer which defines the thickness. So whenever you put two glasses sandwiched together, your thickness should be as uniform as possible, otherwise you will end up with the air bubbles. So thickness should be extremely uniform, that's the challenge. So we don't have that kind of technology. We can make it in a lab scale 2 centimeter by 2 centimeter, 3 centimeter by 3 centimeter. But when you are talking about 3 meter, 5 meter, 8 meter, it's really difficult. And also we are working with 0.5 micron kind of thickness. It's extremely difficult. It's even if you make little mistake, glass will break. So how to sandwich these glasses? The spacer should be whenever usually we are using glass spacers that should be uniform. Then this is the very important layer, the alignment layer. So whenever you are talking about liquid crystal technology, alignment layers are extremely important. So far we have used the rubbing technology, but world is changing. You have seen the Apple's all-in-one where they use the photo alignment technology, where they are aligning the molecule with the help of polarizing UV light. It's a special kind of polarizing UV light. And again, when I am talking about polarizing UV light, you need such kind of alignment layers. The chemistry, physics, mathematics, everyone should work here because it's not easy to create such kind of material. So very strong chemistry people should synthesize such kind of alignment layers where it will work with the polarized light. So when you can align the molecule either parallel to the polarization direction or you align perpendicular to the polarization direction, then you send the liquid crystal in between that. So beauty of liquid crystal is it will just follow the surface direction. If it is parallel, liquid crystal will also align parallel. If it is perpendicular, it also aligns perpendicular to the light. That's why photo alignment. Why photo alignment technology is important? Because you are not touching the surface here. Your light is doing the job, because available technology we are touching the surface. It's a rubbing technology. So whenever you are talking about rubbing technology, there is always a static charges are present. So there is a chance that your display might go bad after 5 years, 10 years. But whereas photo alignment, since you are not touching the surfaces, the resolution is extremely good and life of the displays are also good. It's a common thing. How displays function here? Your polarizers here, two polarizers which is crossed each other. You are shining the light and you are not switching on the electric field. Light is transmitted as a basic physics. Then you switch on the electric field, you can see here. So liquid crystal molecule align with respect to the polarization direction, then light is blocked. Light is blocked in the sense you got the image. That's the simplest way of getting the liquid crystals. So why it is called liquid crystal? Because so many of students are here. Why it is called liquid crystal? It's a intermediate state between solids and the crystal. Why solids and crystal? Because it is taking some properties from the solid, like position order, orientational order and birefringence, which is from the solid, and also it is taking some property like a flow from the liquid. So it's a combination of solids and the crystal. Because of that it becomes liquid crystal. Because of that only it is very important, because since it is moving, it is flexible, you can tune this molecule the way you want it. Whereas if you take directly crystal, it's not easy because you have to apply very high electric field to tune the molecule. but because of they are moving, you can easily, they can tune those kind of molecules. How these materials looks like, if you are in a crystalline phase, you can see how the texture looks like, how the molecular orientation looks like, how the position looks like. Whereas if you come to the liquid crystalline phase, it is a more ordered, called as a smectic phase, it is a layered phases. You can see the order is also almost like these kind of orders. Whereas if you come to the pneumatic, that is where all the display industries is working on these kind of material. Pneumatic liquid crystal has been used in the display industries, where how to identify these pneumatic, it exactly comes in a 2 brush and 4 brush pattern. You can see here, if you put your this one here, and then there is a 4 brush, there is no 3 brush, there is no 1 brush. It's like a defined one. 2 brush, 4 brush pattern is a characteristics of pneumatic liquid crystals. So then again, it's a more random orientation compared to the smectics, but they are not completely random like isotropic. So isotropic is completely like a liquid. So how to synthesize them? There is a 2 part. One is a hard part, which is called as a core of the liquid material. You can see first you have to take the core, because lot of patents happened on the cores. They may create the cores and they patent it, and those kind of cores you have to put all the soft units. Why soft units is required? Because if you just use the core, your temperature will go around 120, 130, sometime 200 degree, but you cannot operate your laptop at 200 degree. You want to operate at minus 60 to plus 60, like Siberia to Saudi Arabia. So those kind of places you need these kind of materials. You have to reduce the temperature of the liquid crystal. So there is millions of liquid crystals synthesized, hardly 20 to 50 materials are room temperature out of millions of liquid crystals. You just see how complicated this technology is. If you are having such kind of material which gives from minus 60 to plus 60, within no time you will be billionaire, because so many industries are looking for such kind of liquid crystals to put it in the display division. So this one cooked noodles, it's calling, it's a flexible chains which will reduces the temperature of the liquid crystalline materials. And again, characterization, it's a simple polarizing optical microscope. If you have these POM setup at your laboratory or in your company, just observe the phases, what kind of phases it exhibits. Then again, differential scanning calorimetry will tell whether they are liquid crystalline or not, and XRD will tell which phase you are in. So these are the future applications already there. Electrochromic and even PDLCs, polymer dispersed liquid crystal, has been used in the switchable windows. It's a different kinds of application which are going to come. And this is the microscopic view. You can see within 20-25 seconds, you can see so many different kinds of liquid crystalline phases. One is chiral. There is a lines, which is a focal conics, comes with the horizontal. There is a line which is called as a chiral molecules. Again smectics, again pneumatic, again you can see the chiral lines. It's not easy. Even if you miss little bit, within 1 second, if you turn your eyes, you will miss certain phases here. It's a very interesting technology. When you sit in front of the polarizing optical microscope, you have to closely observe the phases. Otherwise, within fraction of a second, you will miss some important liquid crystalline phases. And this is some interesting application made by the Hanna group of Germany. The ladies, this one, nail polish. It is with the cholesteric liquid crystal. You can see it's already in the market.
Hi, it's Hannah, and I just wanted to start out with a quick disclaimer. When I filmed
So
this video, I was so excited because this
so
effect
you have to
looked
put this
so
material
cool, so I really
based
rushed
on
into
your
it without
mood.
being fully
The nail
educated
polish
and
color
made the
also
mistake
changes.
of using liquid crystal
And
over
again, the
regular
same
polish.
company is coming
I
with
reached
the
out to
sandals
company and they
with the
state
same.
that it's for use
So
on
Bluetooth
artificial
they
nails to
connected.
be on the safe
So
side,
based on
even
your
though there
dress,
are no known
you can change the
complications at
sandals
this
color.
time with using it in nail
Again,
art. I wanted to bring
from the
this to
liquid
everyone's
crystals,
attention since your
cholesteric liquid
safety
crystal, they are
is
changing
super
the sandals
important to
color
me, and I
based
don't
on
want you
the
to make the same mistake I
your
did. I
dress
love
color.
trying out new.
Then again, the two important aspects here in display. One is the how light is playing role, because light is extremely important in these kind of technologies. So when I am talking about light, there is two effects. One is the bulk effect, where the display is happening. All the display which you are doing is a bulk effect. One is the surface effect, where I am talking about photo alignment technologies. When we are talking about light, when we can using the bulk effect, we can write the advertising boards, digital boards, then electronic paper, whereas surface effect can make the name cards, ATM cards, electronic books and all. So this is how the bulk effect taking place, where you are having the azobenzene molecule, which is a light sensitive molecule. So, take the azobenzene molecule, we all know that these azobenzene molecules are the trans shape looks like a rod shape, and when you shine the UV light of 365 nanometer here, this rod shape molecule becomes the bent shape. This is the basic physics we studied in our PUC classes when you are talking about isomers. So, here what you have to do is you take a very small percentage of this azobenzene molecule doped with the 95% of the liquid crystal, make it as a guest host system where guest is azobenzene, host is a liquid crystal. So, when you shine your light to such kind of molecule, your red is azobenzene and green is a liquid crystal. So, liquid crystal, because of your shining the light, liquid crystal is going to the isotropic phase, which is randomly oriented, whereas your rod shape becomes the bent shape. Under the cross polarizers, this shape, the isotropic becomes the dark because of the cross polarization, whereas other phase it becomes the bright. So, you have a very perfect dark and bright combination. So, you can create the optical images. If you are sitting in the bright state, put the mask, whatever the image you want, you shine the light to that, whichever the material seen the light, which goes to the dark state, which is homeotropic, whichever you have masked, which is still in the bright. So, you can write the images, you can create the optical images by using these kind of technologies. But again, exception to this, in nature, whenever you are working on these kind of liquid crystal material, in nature, the nature rule is if you disturb the order, it always goes to the disorder. But if you disturb the disorder, it is not necessarily that it should go to the order, right, like a classroom. When teacher enter into the class, it should be ordered, but before teacher entering the class, it is randomly distributed. But exception to this, we reported in 2004 in advanced material, where we showed that even if you are sitting in the disorder phase, when you shine the light to that, disorder can go to the order phase. You can see the border between order to disorder. So, we sat in the nematic phase, when you shine the light, we enter into the smectic phases. So, that we use the re-entered nematic phenomena. This is a one exception along with the natural law compared to these kind of displays section. Then again, we created lot of displays from these things, which various material we synthesized more than 200 such kind of light sensitive material in our laboratory. Then we created such kind of displays here. You can see the bright and dark state here. Then we write these kind of images on the glass. It is a very small 2 centimeter by 2 centimeter display. Again, in collaboration with Image Labels, Bangalore based company, we did, and these are the molecules we synthesized, where you can see the azobenzene is here, then long chain is here, which taking care of the temperature of the material. So, another interesting phenomena in this kind of material is the dual frequency. It is not necessarily that you have to go to the isotropic. So, whenever you are going to isotropic, you are sending the molecule to the random position. So, whenever molecule is randomly distributed, it is not easy to bring back to the original distribution. It takes time, and you have to apply large electric field to that. So, there is another concept where it is called as a dual frequency addressable. You do not need to go to isotropic. With the frequency only you can tune. You can see the positive delta epsilon is here, negative delta epsilon here. Just by changing the frequency, you can go from bright state to the dark state. How to do that? You can see here, when you apply the low frequency, which is 60 kilohertz and 30 volt, it is a UV off state, you are in a dark state. Increase the frequency to 180 kilohertz, you are in a bright state. Then again you switch on here, here light is off, but frequency is increased. Put the electric field on, you are in the dark state. You do not need to go to the isotropic. Just by playing the frequency from positive to negative, you can able to get the display here. So, this is the one display we created here. This is the mark. The standard 1951 USAP mask has been put on top of the glass displays, and you can see how the mask has been written here. It is a permanent displays. The next technology is the photo alignment. It's already I shown bulk effect. Now is the surface effect, which I already told. It's a non-contact method of creating the display. What are the main problem here? There is a lot of companies working on this kind of material. The biggest problem in this kind of material is material cost is very expensive. Material cost is very high. Photosensitivity is very important because we are shining polarized UV light to this kind of system. Fabrication steps are more, and transportation of the material, because available material mainly we are using polyimide material, and polyimide you have to store it at -10 degree, and with this -10 degree you have to purchase this from Japan. Nissan Chemicals is the biggest distributor of this kind of polymer material. You have to take it at minus 10 degree from Japan to other countries. That cost is very high, and adding to that, the lifetime of this kind of material is only 6 months. After 6 months again you have to purchase. So that is why photo alignment materials are having bigger advantages, because they are coming in a powder form, not on the liquid form. So whenever you want to make a display, you dissolve these powders in a required solvents like UPAC defined solvents like PGMEA or DMF or NMP, whatever the solvents. Then you can align them, you can spin coat them on the glass substrate, then shine the light. So then it will align either parallel to the polarization direction or perpendicular, depending on the what kind of molecule you are using. What are the criteria for aligning these kind of molecules? First is the chemical stability should be very high, because later you have to transport this to the different countries or different fab facilities. Solubility should be good, because we cannot work on chloroform kind of solvents. Adhesion, because you are spin coating, so it has to adhere to the glass substrates very well, it should not come out. Convenient preparation of both monomers and polymer. Reproducibility should be good. Low levels of ions, because when you apply the electric field to that, there should not be any ions should generate, otherwise it will disturb your display properties. And alignment properties should be independent of your thickness, polymer thickness, and most important thing is long shelf life. How does it work? Take a photo alignment material, coat it, exposure with polarized light, and you can see the molecule is aligned like this. Fill the liquid crystal will align to the surface directions, and it is called as a nano photo alignment, because the aligning size is around 50 to 80 nanometer. That is why it is also called as nano alignment technology. So what are the parameters you have to understand when you have such kind of photo alignment, which is the future technologies? So when you have such kind of technologies, you have to measure the order parameter present in them. So very simple to measure the order parameter. You have you can see the equations here. So if your order parameter is equal to 0, that means it is a randomly oriented. If your order parameter is equal to 1, it is parallelly oriented to the director. If your order parameter is equal to minus 0.5, it is parallel to that, perpendicular to that. So your value should be minus 0.5 and 1, those region. If you are creating the molecule which is parallel to the director direction, then you have to work for 1. If you are creating the molecule which is perpendicular to this, then you have to work for minus 0.5. How to measure this order parameter? Here A and D is same, do not confuse with this A. This A and this D is same. Take a glass substrate, coat your layer, take a simple UV spectrum, there is not special equipment is required. Take a absorbance spectra, initially like this, put a polarizer in between, then the material split into two parts. One is the D perpendicular, which is a perpendicular component, one is the parallel component. The ratio between the two is giving the dichroic ratio, the way you are making polarizers. Higher the dichroic ratio, better is your polarizer. Higher the dichroic ratio, better is your aligning material. So make sure that your dichroic ratio should be good with the synthesized material. Then you have to measure the anchoring energy, which is again important parameter for the display industry. And here we have measured the azimuthal is like this, polar is like this. If your this anchoring energy is extremely strong, then this is much stronger, because it is not easy to move the molecule from this state to this state. If this state itself is very tough, this is extremely tough. So people are usually measure the azimuthal, they won't measure the polar. If you have the facility, you can measure the polar anchoring energy. How to measure the azimuthal? Take the K22, which is the elastic constant, twist angle using the microscoping, my polarizing optical microscope, put that into this equation, you will get the azimuthal anchoring energy. Again, to make that kind of azimuthal anchoring energy setup, you have to make a twisted nematic cell, which is twisted 90 degree with respect to each other. These are some of the materials we tried initially. We used the azobenzene molecule. I already told azobenzene will bend when you shine the light, but these are the certain material where it won't bend, it just reorient. Why it is reorienting? Because there is a two azobenzene molecule, if one goes up, another comes down. So when you measure the anisotropy, that is why my talk is about shape anisotropy. So when you measure the anisotropy of these molecules, they are the same, they won't change. Because of that, they are aligning with respect to the light. But again, it is not true for many molecules. Only out of 100 molecules we tried, only these 4 or 5 molecules we got such kind of anisotropy. But all other cases, azobenzene is completely bent. So these are the wavelength. I am not touching here. These are the dichroic ratio and order parameter measured. You can see that the material called sulfuric dye, this sulfuric dye order parameter is some very close to the minus 0.5, which is what we are looking for the industries. Then again azimuthal anchoring energy, which is acceptable range compared to the market. This is the new, this we worked with the Nissan chemicals. So this is the funded by the Nissan, where it has been implemented by the Samsung, where I was working with the Sweden. We did this kind of concept of nanostructure surfaces. This technology is available for selling. We are working with the different industries to sell this technology, where what we did is we created such kind of cores and we put the planar aligning like this. Then we put one VA material. One is a planar aligning, one is the VA. Then we mixed them together. One part we took from here, another part we took from there. Then we put it as a tilted alignment. So even if you want tilted alignment, 1 degree tilt, 2 degree pre-tilt, 3 degree pre-tilt, we have the technology. If you want homeotropic to planar, then we have these kind of molecules. If you want planar to homeotropic, we have those kind of molecules, which we called it as a new generation VA materials from homeotropic to the planar alignments. So these are the design strategy we followed. First is the robust main chain we selected, which can solve with all the solvents. Side group, which pronounce the shape anisotropy for promoting vertical alignment and also increasing the solubility of the polymer, we use this side group. Then controlling the properties of the polymer main chain, ion traps, anchoring strength. We took care of all these parameters when we are designing such kind of molecule. So advantages of our material, it can dissolve in most of the solvent. This TG is greater than 200 degree, very long shelf, because we synthesized this in 2008 and until today we are using this molecule in our lab. Nothing happens because you have to store it at room temperature. They are coming in a powder form, just you have to mix with the solvent and you can study. So these are the one display we created in the lab. I don't know whether it's. Yeah, this is the one flexible display we created. We took the 2 plastic sheets, conducting plastic sheets. We wrote these images inside, and we just, you can see the how much you can bend here. It's a very thin substrates, and even after bending until this angle also, display remains intact. It's not changed at all. So that means material is highly stable, and you can able to take this technology to the bigger display industries. The next one is permanent photos, which is work with the tri-stable switching, where you don't need to go to the isotropic. You can go to the, this is not a dark state, we painted on the back side. So tri-stable switching, you can see that state, this state. In between, if you tune your electric field, you can able to write this butterfly. So this, if you put your picture like this and you can remove the electric field, unless or until you won't apply the electric field, your photos remains like this forever, even for 100 years, it won't change at all. So this we have written in 2007, until today it remain in the same contrast. The next is quantum dot. We all know that nanomaterials and quantum dots are the future, because 2023 Nobel Prize is on quantum dot. So we have to mention this technology, because this is the guy who changed the universe, how we are looking at, and there is a lot of things we can do with these kind of quantum dots. Again, lot of opportunity to synthesize quantum dot materials. Not only one synthetic methods, there is thousands of synthetic methods to use quantum dots. Lot of opportunities in coming days where we can able to make very good quantum dots. Again, the nano and quantum dot, if you mix such kind of carbon based porous material, if you make a porous quantum dots or porous carbon material, if you mix with the liquid crystal, you can able to increase the birefringence, which is again required for the industries. You can see that when nanoparticle size decreases, birefringence increases, which is again the bigger advantages for the industries. And in summary, the displays are very essential for us, because we are heading to that. We have to bring all this technology to our country. So we need a lot of manpower, because specialists are required. I think workshop like this will really throw a light on all of us, how we have to go forward and what kind of speciality required and what kind of manpower required and what kind of technology you have to bring. All these things can be discussed during this kind of platform. And one last, the nature itself is a beautiful display. You can see it's a cholesteric liquid crystal, where you can see that whenever the mood changes, you can see the color also changes from the bird. This is the cholesteric liquid crystals. So before concluding, I would like to press this, in spite of all the technology, because we are talking about such kind of technologies where toxicity is also a part and parcel of the technology. We have to get the toxic material, because when we are talking about quantum dots and all, there is a toxic material involved. We have to make sure that we have to handle this material very well. If Darwin's theory really holds good, when man was like this, earth was like this. When monkey becomes man, earth is like this. So we should not take our earth to this way in the name of digital technologies. So I thank the LCNA and all the organizers for giving me opportunity, and also my funding body for this work, VGST, Vision Group of Science and Technology. They are also one of the sponsors, one of the organizers. They have given money for conducting this photo alignment technology. Thank you all.
Mind-blowing presentation. What do I say? So that was a mind-blowing presentation, Guru. I really freaked out on the work that you're doing, and the way you have presented it, it's amazing.
Thank you.
On behalf of this audience, on behalf of LCNA, I really must thank you for it.
Thank you, sir.
My pleasure. Here's a small token. Thank you once more. Thanks. Catch you up. For the next session, I will be introducing a different speaker. Dr. Sudhir, are you there? Okay, let's see how to make the connections up. You're loud and clear. Just give me a minute as I introduce one more leader here while they're setting up your presence on the screen. Okay, Dr. Sudhir is coming on live on the screen. Can I also take this opportunity to introduce Ratnaji? Ratnaji is from Society for Information Display, US. She has actually taken the opportunity to come down and be here in this workshop. Ratnaji will be available for all the students. If you have any queries on the student membership, she will be available during the lunch break. Please feel free to get your queries answered by her. And thank you, Ratna, for coming in for this. Really appreciate this. Sudhir, you are online. So let me do a quick intro. Dr. Sudhir is a mentor for me. He's he's the CEO for the National Center for Flexible Electronics, very deeply engaged with the technologies in this ecosystem. He will be taking over and presenting a view on the display technologies, the OLED and LCD. And as you know, this particular subject is a part of the electives that have been cleared by AICT. So I will invite Sudhir to take over and take you through this particular session. Sudhir ji, your audience.
Yes, please. Okay. Thank you. Thank you, Ashwini ji, for a nice introduction. Can you hear me very well? Okay, very good. Thank you. First of all, I would like to thanks to LCNA and all the organizers for inviting us for this wonderful interaction with the wonderful audience. I could not be physically there because of my personal some emergency at home, but we will try to basically explain from the distance through the slides the subject which was given to us by Yaswini. Thank you very much, Yaswini. The topic for the discussion today is OLED and LCD display technologies. We have divided this topic into 4 sections. The first 2 sections, I would like to give a brief overview about the center and the display activities mounted at the center and the facility and platform, basically the technology platforms which are running at the center. The third, we will go to the display technology and we will restrict today ourselves on OLED and LCD. So what we will do that, we will give a comparison, a little bit about the technology, and we will do the deep down in the OLED fabrication, really the device fabrication. We will try to show you some live slides, how the OLED devices are getting made, and then we'll enter into the emerging application of the OLED. And if the time permits, we'll take some questions. So that's the structure which we have made for the presentation today. I have one of the OLED hands-on expert with me. So maybe the technology in the display technology, I'll invite him to give you a brief tutorial on the device fabrication today in this session. First, let me give the brief overview about the center. I really do not know how many of you know about the National Center for Flexible Electronics. The National Center for Flexible Electronics is announced in 2015 by Prime Minister Modi ji from Talkatora Stadium, New Delhi, and it is fully operational. It became operational in year 2019. If you see the structure of the center and even the mandate of the center is the bridging the gap between academia and industry, okay, ecosystem, and how the center functions. You see the 2 blocks, the left-hand side block and the right-hand side block, academic ecosystem and the industrial ecosystem. Somehow this cursor is not working. Okay, that's fine. So the academic ecosystem, generally it has been seen, or we see in our regular life, lot many technologies are getting developed in academic ecosystem, but they are not reaching to the industrial ecosystem because industry expect that the technology should be manufacturable in a year or 2. That's what the industries are betting into. In academia ecosystem, generally the technologies are developed up to TRL2 or TRL3. Then somebody has to work basically to take the technology to the industry, and that's where the NC Flexi comes in the white block, which generally we call is a valley of death of any technology if it's not reaching to the industrial ecosystem. So what the NC Flexi is doing, taking the knowledge from the academia or academic ecosystem, converting that knowledge into the proof of concept and creating the prototype to that stage where industry can take easily for the manufacturing. To do that one, the NC Flexi has a dedicated infrastructure, is a full green. The center came out from the green field. So you have the full infrastructure, means equipped with the equipment from the lab scale to the prototype scale and the industry scale, so that you can really check the cost of ownership of any product which the industry is going to manufacture and in the center itself. So it becomes easy for the industry to increase the footprint only and manufacturing or the technology transfer easily from the center to the industry. Parallelly or simultaneously, the technology which is getting developed here, and then the prototype or products is going out to the industry, so that parallelly the another mandate of the center is to develop ecosystem in the equipment design and the material innovation as well. So I will give you the brief details in the following slide as we go along. The focus area of the center, if you see the 6 blocks on the top, these are the technology platforms mounted at the center. The first block, the TFT, thin film transistor. Let me give you the preamble that anything and everything what we are doing here in the center, we are doing on the flexible substrate. Substrate may be the plastic, maybe paper, or maybe cloth, but it is a flexible substrate. That's what that the center say, the National Center for Flexible Electronics. So the TFT, when I say we are printing the TFT on the flexible substrate, generally it is going for the application of the defense application, DRDO or ISRO at this scale, very specialized application. Then second one is the OLED, which we will go into detail today, basically the display technologies. And that is too, we are driving into the printable displays. So the cost of the displays goes down and you can scale easily. That's the effort what we are trying to make here. The third one is the photovoltaic. Again, the photovoltaic, printing the photovoltaic on biodegradable substrate. And in our case, we are trying to print the displays on the paper. That's basically some niche devices. You can take it and the printed use for year or two and then recycle it. And the fourth one is the sensor. Variety of sensor, but mainly working in the sensor in the healthcare sector. The fifth one is the material, because if you print anything or you are making any device or any component, the three things are very important: material, equipment, and the process. And material is very difficult to get because you will not find that the material which you need for the frontier research easily available. You can buy from anywhere, so you have to develop your own material also. So we have a very strong group for the material. And the sixth one is the printed batteries. We are working on the printed batteries, and we have added one more block this year, which is the encapsulation. Then the story remain become complete. So you are making the component, you can make the devices for starting to the end, and you can encapsulate, and you can make basically to a product which can be easily given to the industry. But these are the technology platforms. To combine these technology platform, we have another group, which is the system integration group, because any product or any prototype needs the multiple of the components, multiple of the devices to integrate together, and serving to the sectors which you see in the below in the slides. Memory and logic circuit, which is going for the strategic sector, especially for the defense sector. Then healthcare, especially I would say the wearable electronics, the sensor or point of use diagnostic, that's the sector we are serving. And then solar, we all know the solar. And then display, very deeply we are working the OLED technology, which we'll dwell with in the upcoming slides. And then anti-counterfeiting technology. This technology is already out in the market. And the last but not the least is the smart packaging. The smart packaging, what you see at your even home every day, that you need a lot many things where basically your food packaging especially can be made very smart, so you know before opening the packet whether food is good or bad, whether it is a sensor or some display mechanism. So I will just explain in further slides what are the technologies are getting developed in this sector. When I talk about the OLED, organic light emitting diode, we have a very dedicated facility at IIT Kanpur called CEMTEL Center for Display Technology, established in early 2005. And I'll give you the brief detail where that all the facility of fabricating the devices is there. If you give you the snapshot of the Central Center for Display Technology, it is a complete end-to-end fabrication and testing facility, starting from photolithography, fabricating the TFT backplane, and fabricating the OLED devices, then integration of the devices and testing it out and making a full-fledged prototype for any application, whatever basically is feasible or you can dream of. That's the facility under one roof is existing at IIT Kanpur. This OLED can be made by a conventional route, which is the vacuum evaporation process, and a lot many researchers, scientists are working on the printing route. Basically, not everything can be printed because the solution materials are not that available, not advanced at this stage. But yes, in coming years, you will see the printable displays also. Even today, some of the applications will show you that you will see the printable display. Moving to the next slide, just to give you the basically brief about the NC Flexi. So it's a state-of-the-art facility. I would say the equipment from lab to fab. When we say lab to fab, we have a lab scale equipment, we have a prototyping equipment, and then we have an industry scale equipment. Very rare you will see these kind of equipment set under one roof. What does it mean? You can come with the idea, or you can enter with the idea in the center, and if that is workable, then you can go out with a device or a product in your hand. Basically, that's the infrastructure is set up under one roof. And to do that one, all the characterization, material and electrical characterization facilities also under the one roof. And that's the Right hand side, we see the structure, basically how the things are placed. It is a 6-floor, 2-tower building, approximately 5 to 6,000 square meter, where we'll say the 100 crores of worth equipment there. Now, giving you just a OLED evolution, how basically it started and where are we today. So if we see the 1987, yes, the first OLED devices was published by Kodak, and the first commercial passive matrix OLED was announced by the Panasonic, which you see the right hand side in the stereo. That was basically launched at that time. The first commercial active matrix device of the OLED is launched in 2005, and the 2005 at the same time frame, basically the OLED program was mounted at IIT Kanpur with the help of the government and academia and the industry, which was SAMTEL at that time, and then which is the SAMTEL avionics at this point of time. Basically, it is still running. The first India passive matrix OLED was made in 2007. So technology was developed well in time in the country. It is unfortunately that there was no industry at that time. And then as we know that under the semicon policy, the display is one of the vertical, very important vertical. We might get a very good news that display fab is also coming in this country. I think the government is taking very serious steps there. It might be that by coming year, there might be decision on the display fabs. In the left-hand side, you see that from the dot matrix to the foldable, you see the foldable phones today, which is made by OLED, rollable TV, all those things. So for dot matrix, rigid to the foldable, flexible, thin, which we will give you the details in further slides. That's what the OLED roadmap is. The OLED R&D journey at IIT Kanpur is starting from 2000, that when the center got established, somewhere, as I said, that 2007, that first passive dot matrix fully functional industry scale was demonstrated. And by now, if we say that we have traveled the journey from commercial or conventional route to the printable route, where at the end you see the inkjet printed OLED, where the different safe you can just print it very low cost, and the various application, even you can use like a display level in many or variety of packaging. Just to give you the little bit flavor about the market, why that everybody is so interested in this OLED development and OLED market. The 2023 market was closed around 45 billion, and in next 6-7 years it is going to be double, around 90 billion dollars. So there is a lot of interest, lot of applications are coming up where the OLED is capturing the space of the LCD. When we will go to the technology, we'll explain the technology, and then we'll tell you how the OLED and why the OLED is capturing the space of the LCD. So OLED is the upcoming technology which is surpassing the LCD market. If we see in 2024, the 53% share in smartphone display market is by OLED. That is more than LCD. And then going forward, in the small form factor, we'll see more and more OLED. Even for the big form factor, we'll see the more and more OLED screens because the cost structure is going down with the further development in the OLED. Now, the platform, the key platform, what is available even today, and a lot of development is happening. One is the conventional route evaporation, as I explained you, so that by conventional route we can make the variety of the OLED prototype or OLED display, be it passimetric, active matrix, lighting panel, or the display for automatic display. Then there is a partial printed, because going from conventional route to the printed route, it is not that easy. You cannot print all the layer easily by printed route. So whatever the layer you can print to reduce the cost or make it faster, we do it by printing, and the layer which we cannot do by printing because the solution process is not established or the material is not available, then we do it by evaporators to make a partial printed OLED as shown in the figure. The last one is the fully printed. Fully printed is a great potential in the future. If you are able to do the fully printed display, then it will be again the revolution in the OLED journey. Then it will reduce further the cost drastically, not only the product cost, but in the, basically fab cost, it will come the billions of dollars to the millions of dollars. So that will be the scale when it becomes successful. And a lot of people are working towards that. With that one, I would, and this arrow, what I am showing, that basically we go back and forth both with both the facility, because both the facilities are very high tech and equipped here to do it conventional route to the printed route. With this one, we will enter into the technology slides now, and I will invite my colleague, the Madhu Sitaraman. He will give you the deep down in the technologies, where both the technologies, we will compare it. What is the LCD, what is the OLED, what is the difference in LCD and OLED, and then we'll go in detail that how the OLED device can be made and what has been made already here. Yes, Madhu, please.
Hello, good afternoon all. I hope you are having a good session at Bangalore. And just as Dr. Sudhir was mentioning here, so we have a lot of activity going on at IIT Kanpur. And before that, we will have a overview of how the LCD, that's a liquid crystal display, and the OLED display actually works. So coming to a basic comparison of a LCD and a OLED, if you look at the LCD, it's actually a structure where we have a backlight, and on top of that we have a polarizer, and also on top of that we have a TFT backplane array, which is actually controlling the liquid crystal layer, which is actually kind of a flip-flop kind of structure for getting the light in and out of the structure. And on top of that we have a color filter which defines the red, green and blue colors. So all the whole thing comes together, becomes a bulky package. And here it's actually not a self-emitting technology. So you have a backlight, which is typically a LED with a waveguide, which gives a uniform diffuse light. And because of that, the whole structure becomes a bit bulky. So when you compare that with the OLED, it's much more thinner. It has much more small form factor. And if you look at here, we have on the left side bottom, we have the structure of the OLED, where we have the substrate, which is actually a glass substrate or a plastic substrate. And on top of that, the device is built with a TFT backplane, and the OLED fabrication is done on top of that. And the whole thing is packaged with an encapsulation, which actually protect the layers from the atmosphere, basically from the moisture and the oxygen levels. And on top of that, we have a polarizer, which increases the ambient contrast ratio. So if you look at, compare these two figures, you will get an idea about how thin the OLEDs are. And when you compare to the characteristics of this OLED and LCD, you'll see OLED have a high contrast ratio, and LCD has a reasonably good contrast ratio, thanks to the maturity of the technology. People have been working for so long. And also the biggest advantage of OLED is it's a viewing angle. We'll come into detail on that in the further slides. Meanwhile, the OLED has a really thin form factor, which makes it really thin and also lightweight. And the response time, which is a huge advantage with OLED, it's typically in microseconds. So it enables fast switching without any display or the image lagging. And when you compare the OLED screen with the LCD screen, the power consumption is much similar when it comes to the sizes. And another advantage is the custom design. The OLEDs can be custom designed with 3 form factors, but the LCD is basically on the rigid glass. It limits the application and also the design factor there. And lifetime, the OLED wise, it's improving over the years. And typically we are looking at around lakhs of hours right now. And cost wise, right now the OLED costs are slightly higher, but over time, with the efficiency and more material coming in and going to mass production, it is also going to coming down. So it's not a straightforward comparison between LCD and OLED, but it's a kind of how the technology is different from one another. And coming to the contrast ratio of OLEDs, when you compare that to LCD, you'll see that the contrast ratio is much higher in OLED because it's a self-emitting technology. So it doesn't require a backlight. The pixel itself emits. So it will give a really good black screen when it's off. So that improves the ambient condition or ambient contrast ratio. And also with higher brightness, the contrast ratio actually improves when you compare that to the LCD. And also, as I mentioned, it's a planar light source. That's a Lambertian behavior kind of light source, which gives a really huge, wide viewing angle, typically in range of around 180 degrees, 180 degree, sorry. So, and this particular viewing angle is maintained even at different temperature ranges. So it can go up to really low temperature and also to really high temperature as well. So it actually gives a window of lot of applications. And another advantage of OLED is the response time. So the response time of a OLED is in microseconds, and compare that to LCD, which is in milliseconds. So it actually enables faster frame rates, and also it actually gives a really crisp and really clear images when you are going for high speed or high frequency frame rate applications. And this particular OLED advantage is actually continuous throughout the temperature range also. So when you look at the LCD screen operating at lower temperatures, it has a tendency to cause image sticking and other problems. But when you compare that to OLED, even till minus 40 degrees Celsius, it has a really consistent frame rate. And let's talk about OLED, how it works. So OLED is actually an electroluminescent device based on, it's a diode device based on organic materials. So here we have a substrate. On top of that, we have a transparent conducting electrode. And in between, on top of that, we have a lot of organic layers, typically in the range of nanometers. And on top of that, we have a back electrode, that's we call typically the cathode, which actually could be conducting, and also it's actually conducting, and it's can be transparent, reflective, or even opaque as well, depending on the different applications. So here, when we are biasing it, the electron hole pairs actually come from the anode and cathode side and combine in the organic layer, and it emits the photon. So that's a basic principle of how OLED works. And why we are working on OLEDs? So OLEDs are actually a solid state light emitting device, and it uses organic materials, and it gives a lot of options when you are looking for a particular color or particular efficiency. And another key advantage of OLED is the planar light source, and it's really glare free, and also it gives a really uniform diffuse light output. And another biggest advantage for OLED is it actually doesn't have any UV emission. So with the organic molecules, you can actually fine tune the emission wavelengths and avoid the UV emission there. And another advantage is the low heat up because of the planar light source. It can easily dissipate the light. It doesn't need any extra heat sink or any other compensation mechanism for the OLED when it's operational. And again, I've been mentioning regarding the thin form factor, that's a huge advantage. And not just because of this qualities, OLEDs are widely adoptable right now. Another key advantage is the substrate, a range of substrate on which the OLEDs can be made. So it can be made on glass, it can be made on plastics like plastic substrates like pen, PET, PI, and even on synthetic textile fabrics, and also on metal foils. The only criteria here is that the surface should be smooth enough so that we can put all these layers which are typically in nanometer range. And also it actually really beneficial when it comes to processing as well. So when you look at the OLED fabrication, it can be done in different ways. So the conventional way is the vacuum thermal operation, and that's a widespread and widely used in the industry right now. And typically right now, all the OLEDs or the OLED screens which are in TV and also in your mobile phones are made through the conventional process. And another different process which are catching up is the printing technology, which we are also pursuing here at IIT Kanpur. And also we have the inkjet printing here, we have the slot die printing here, then we have a new technology called organic vapor jet printing. That's also a new way of making OLEDs. All these things are really beneficial when you are making OLEDs. So it gives a really good overview how we can adopt OLED, and also at the same time it gives you an idea about how good a technology OLED is. And talking about the form factor, the OLED can actually be thin and lightweight. And if you look at the image on the left, the glass used here is 0.7 mm. And it can be even thinner to around 100 micron. There's the flexible glass on the the image in the middle. And you can use plastic substrates also, which makes it bendable and rollable as well. So it can be done, it can be fabricated on a range of substrates, even with a range of thin form factors. Now we will come to the OLED fabrication and emerging applications. So here we will be briefly touching on the vacuum thermal evaporation, that's a conventional route. And also we will talk a bit about the printing of these OLEDs as well. That's a new route which we are undertaking here at IIT Kanpur. So the broad overview is that suppose we take a substrate. The substrate can be a glass substrate, which could be rigid or a flexible one as well. Or we can use a plastic substrate like PET, pen or polyimide substrate as well. And on top of that, we will have a transparent conducting electrode that will be usually ITO, indium tin oxide, or indium zinc oxide or aluminum zinc oxide. And to add on to the conductivity of these layers, we usually use a metal layer, which could be chromium, molybdenum, based on the addition and the conductivity requirements of these particular devices. And this is a start substrate which we use for fabricating the OLED displays. So we will pre-clean these substrates through different processes, make sure there are no particles there. And once it is done, we coat the photoresist, which is the typical photolithography step, where we coat the PR, pre-bake it, then we use a photomask, which will actually expose the photomask onto a PR, which gives us the patterns, and we will develop these patterns, harden the PR by post-baking, and then etch out the areas which we want. And once it is done, the photoresist is stripped, and the whole cleaning procedure is repeated so that we can get really crisp and fine features. And we dehydrate the whole substrate and do the inspection. And this whole process of photolithography is repeated based on the number of layers we have in the device structure. And this same procedure is repeated for the TFT backplane application also. And that will also require a bit of deposition techniques also that we are not currently showcasing it here because of interest of time. And also once all these processes are done, all the lithography part is done, then we finally pixelate it. The pixelization is actually using a dielectric layer to define the pixels definition. So if you want a display where we have the red, green and blue pixels, you have to define the size and shape of these pixels so that you can do the OLED fabrication on top of it. So once it is done, we have the final inspection, and then the pattern substrate is actually transferred for OLED deposition. So coming to OLED deposition, through the conventional way, we use the vacuum thermal operation, where we load the substrate onto the system through a load lock, and we pump up the chamber, and we actually transfer this particular substrate to a high vacuum chamber. In the high vacuum chamber, we have the materials which are preloaded, and also we have a shadow mask, which we call as the fine metal mask, which is actually aligned with the substrate so that we can create these red, green and blue pixels. And once the alignment is done, we will actually start depositing the material one by one. And for each layer, we need to have a really good stable rate, and also that ensures that we have a good reliability on the layers and also really good uniformity as well. And once it is done, the deposition is done, we unload the substrate and we transfer to the next chamber. So the same process is repeated based on the number of layers on the device, and also how good or how complex the OLED structure is. We'll give you a schematic of that in the next slide. And once this particular OLED deposition is done, we have to protect this device through encapsulation. So encapsulation is the way which we package the OLED to protect it from the external atmosphere. So the OLED being using organic material, they are really not that much tolerant to water and oxygen. So the moment these two elements come in, the device can degrade faster. So to protect the device, for a glass-based OLED, we use a glass-to-glass encapsulation. For the glass-to-glass encapsulation, we actually use a cover glass, which is cleaned. Then we applied the sealant on the edges, and we use a desiccant material which actually absorbs the gases for longer periods of time. And once it is done, we align the substrate and the cover glass together and paste it, and we use a UV curing system which actually permanently seals these two glasses together. And talking about a flexible OLED, we have a technology called thin film encapsulation, which is basically adding really thin layers of typically in the range of nanometers on top of the device itself. This is widely used for foldable and bendable displays on plastic substrates. So for that, we typically use the plasma enhanced CVD technique or the sputtering technique or the atomic layer deposition technique for creating these layers on top of the device. So suppose you don't want to expose your device to these processes once the processing is done, or you can make these barriers on another thin film or on top of plastic barrier, and then laminate on the device to protect it from the atmosphere. So this is the device here is laminated together with the adhesive, which is usually a UV curable or a pressure sensitive adhesive, and that protects the device from external atmosphere. So that's the basic packaging of OLED, how it's fabricated and also how it's protected from the atmosphere. And just to give an overview of the whole thing which I explained in the last slide. So just to visualize it, we have a transparent conducting electrode, and on top of that we have the organic layers one by one. So it's actually a bottom to top approach where it's additive manufacturing kind of scenario here. So we have different layers, and on top of that we have a metal electrode which completes the whole diode structure, and and each organic layer has a different function, and based on the performance, based on the color, based on the efficiency you need, you can actually play around with these different layers. That's the beauty of OLED, because as I mentioned, you can have different colors with a really good color CRI index, and also really good color coordinates with OLED molecules. So once this structure is made, the same thing is repeated for different colors as well. For the display, we need typically the red, green, and blue pixel. So each emission layer is deposited one by one and side by side, so that we can have the overall OLED display. And on the picture on the right, you can see the basic working principle and each layer, how it functions. So we have the Hall transporting layer, we have the Hall injection layer, we have the electron transporting layer, and each has a different function electronically. And also the emission layer is where the light comes out. So basically the electron hole pairs travel through the other layers and reach the emission layer, combine together, form excitons and emit the photons. And this is a typical vacuum thermal evaporator. Here we have the on the image on the left, you can see at the bottom you'll see the evaporation source which have the preloaded material which we want to evaporate. So we actually take pump up this particular chamber to ultra high vacuum conditions, typically into 10⁻⁻⁸ millibar or above, and we heat up these crucibles or the linear sources, and the material gets evaporated. And on top of the chamber, we will see the substrate, which is actually aligned with the metal mask, which we call the fine metal mask for display applications. And in between, we have an in-situ film thickness monitor, which is usually a QCM, which actually gives us the real-time rate and rate of deposition and also the thickness. So by that way, we could actually control the whole process in a really good manner. And if you look at the image on the right, you'll see the actual chamber, where in the bottom you'll see the sources with the shutters, and on top you'll see a hanging bar, which is actually the thickness monitor, and right beside that you'll see the substrate and the mask area where the substrate is loaded for deposition. So that was the conventional vacuum thermal evaporation route. Now we are taking new approach through printing techniques. So the printed OLED is actually much more complex. Just give me something. Okay, sorry. Yeah. So printed OLED is much more complex when it comes to material synthesis, where the materials are limited at this point of time. And once we have the materials, we have to make a ink out of it. So the ink formulation needs to be stable, and it should be soluble in a range of solvents. And also we have to look at something called orthogonality. So when we coat a material, the next layer or the solvent which we are using for the next layer shouldn't wash away the layer beneath. So we have to have that orthogonality in all the materials which we are using, so that we can process and optimize the layers one by one. And finally, we can optimize the device itself based on the performance and also the stability parameters. And once we have the device working, we can use it for different applications, basically for prototyping. We can design the prototypes and also go for fabrication. So if you look at the bottom image, you'll see a flexible OLED which is actually fully printed at our facility. And another challenge here is that we have to look for the interfaces and also the wetting parameters of these particular materials and the inks on the substrate. So we have to look for the ink and also the substrate parameters, the surface energy matching and all those things, so that we can pin these particular ink or drops on the substrate we can get, so that we can get a really smooth film and also subsequently make the devices. And coming to the applications, so OLEDs are typically widely used in mobile phone and TV displays these days, but there are much more applications in OLED lighting and also a new age application which is called a OLED signage. So signage is basically static display kind of application where you can usually typically make any surface emittive. So we'll show you some of the examples in the coming slides. So this is one promising application which we have developed recently at our center. That's the automotive cluster display. So if you look at the typical currently available clusters which are in the motorcycles and also in the cars, you'll see that they are based on LCD. So the problem with the LCD is that it can't work on really low temperatures. The OLED, when it comes to the technology, it can perform on a wide range of temperature. And another big advantage is that being a self-emitting material kind of technology, it can actually create a really good ambient contrast ratio, and that improves the sunlight readability. And it can be done with multiple colors, and at the same time, if you see the image on the right, you'll see that there's not much reflection coming from the device, and that actually adds to the readability in direct sunlight as well. And even looks even more good in indoor and also in low light applications. And taking this forward, we had actually made this technology into a transparent OLED version as well. So that can be used for heads-up display. So typically we change the reflective cathode with the transparent cathode so that it can emit from both sides. And when it's off, you can see the other side of the screen also. So typically if you are using this kind of OLED display on a car windshield or something, you can actually, when it's off, it will just show the outside part. But when it's on, it will show the display, basically that speed, your fuel, all those things, and that could be having really niche applications. And another upcoming application is a tail lamp, which has been recently adopted in really high-end cars like the BMW and Audi. So the current LED-based tail lamps have a disadvantage when it comes to the heat, which is created when it's operating, and it's really difficult when it comes to, there's a good amount of difficulty when it comes to the design and also the assembly part of it. And also it actually takes a lot of space when in the back side of the vehicle. So when you replace that with the OLED, which is really thin and it doesn't have much heat generation when in operation, and also it makes really thin form factors, the OLEDs are currently being adopted in automobile tail lamps as well. And another advantage is that it can give you a lot of design freedom when it comes to the tail lamps, and also it can easily incorporate on the vehicle's body without much complexity. And the same application can be used for interior lighting as well, where you can incorporate the OLED lighting on the interior of the vehicles, reducing the space requirement and also the weight. So here you can see if you have a reflective cathode kind of a OLED, you can easily incorporate that into a vehicle's mirror, and if you want to use that as a light, you can simply turn it on, and when it's off, it looks typically like a mirror or a rear view mirror. Another application which we have developed here is the packaged 7 segment, which we have actually visionized to replace the already existing LED kind of segmented displays. And this is packaged in such a way that it's been done, you can plug and play. So you can take out a LED module and put this OLED module on the same PCB. And here also we have different design freedom, and also we can have different digits, different number of digits put together. It can be even 1 digit or all the way to 5 to 6 digits we can easily incorporate in a single substrate. So this is something which we have recently developed. And finally, coming to the printed OLED space, which we have been pursuing. So here we are using a plastic substrate. On top of that, we are printing each layer, and we are encapsulating with a flexible barrier kind of encapsulation. And you can incorporate that with a flexible battery and practically put it on any surface. So if you look at the image on the bottom right, you will see that it's put on a bottle, and it's really a niche application where you can actually convert any bottle or any window into a OLED surface, which actually attracts a lot of attention. So it can be used for signage applications like static displays, or even for marketing applications as well. And even for safety kind of applications at night, you can use OLED, which can be easily placed on a jacket, which really helps us to avoid accidents and other things. So these are the different applications we are currently working on. And this was a brief overview of all the things we are working at IIT Kanpur, and also how the OLED technology is advantageous. And I think we have some time for question and answers. I think we'll be happy to have that. Thank you.
Thank you. Thank you, Sudhir.
So over to you, Ashwini-ji. If any question from the audience, we can take any question. I hope that the session is useful for the audience.
Oh, Sudhir ji, really appreciate the time you gave us for your presentation on display technologies. I wasn't aware that you had actually created these products already, and just imagine, we are definitely not a barren landscape on display. There's a lot of work that is happening. The discussion I was having with Ratna is what will be echoed by Guru also. We will try and create some pockets of said chapters, which will start focusing on display also as a focused elective area, focused technology area. There are companies in this domain who will be looking at building up their own paths in the country. So Samsung, LG, a lot of these consumer electronic companies will be one pathway which could evolve in this area. Let us see how this will come up. Any questions at this point of time? Any questions? Sushant, please go ahead. Dr. Sushant.
First of all, I would like to thank them for such a wonderful presentation, and also congratulate them for all the technological developments that they have at their center. My question is regarding, you have mentioned that you have all the, you have, while showing the milestones of the achievements, you have talked about the passive matrix OLED. Currently, are you manufacturing all active matrix RGB OLED? I mean, the examples that you showed, are they active matrix OLED?
So Ashwini, so if I understand your question correctly, I think we have shown some of the applications. They are not all, because some of the industrial project what we are doing, when we'll get a chance with the time will show over, but definitely we are working on the active matrix as well. There's some defense application for active matrix, and then we are making some other application also the active matrix displays. There's a full facility here to make the active matrix displays.
Okay, sir, thank you. Some more questions, sir. Sir, you have like you have mentioned the fully inkjet printed OLEDs. Can you say like what are the challenges for you for the fully inkjet printed? Is it only with respect to the electrodes or anything more also?
Challenges still remain with the material, and then how you encapsulate the devices, so that this is coming up. But the application like let's say the packaging or something where you have the shelf life of the product, this is very well going along. And time to come, you will see in the country itself that you will see much more application of the display level of each and every packaging. As we know that by packaging law, the bigger part of or outer part of the cartons are going away. So the marketing or the displaying information need to be done on the article or product itself. So that this market is growing very fast, and lot many companies are dwelling into. So we definitely that it is going alone, but yes, challenge remain the material and encapsulation.
So you are facing challenges with respect to the inks as well as the packaging for the fully.
Yes, yes.
Okay,
yes.
sir. Sir, do you also do the backplane also in a printed method, or the backplane is?
That's a very good question. That's a very good question. And answer to the like a plain vanilla answer is yes. Basically, we do, like I have showed you, the one of the vertical is the TFT as memory. So we do print the TFTs, but yes, specification wise we are not there. It is a journey that has started globally, and then we the facility what we have, that full facility of fabricating the TFT. So yes, we are doing that one. We have demonstrated some of the application, and some of the prototype we have given to the defense application, especially in the ISRO.
Thank you, sir. If I may, is it a IXO backplane for printing?
Yes.
Okay, sir. Thank
Yes.
you. And well, I guess that's all.
Okay,
Thank you so
great.
much for.
My suggestion is let's break for lunch now, and we can have food for thought while we are taking lunch. Okay. Thank you, Sudhir and team NC Flexi for this session. We will connect with you separately in future, and have a great day, Sudhir. Cheers.
Yeah. Before we break for lunch, sorry, there's two announcements to be made. One is, can those come from institutions like academia? Can you just raise your hands, please? No, I'm talking about faculty members. Sorry, faculty members. Just a faculty. See, we'll be having a meeting after the session gets over in the evening. Mr. Sandeep Saxena, additional secretary, will be addressing to you. So we need to get into kind of collaboration. So please stay back for 5-10 minutes, not much of your time. And second request is, see, we want to have some feedback. So it'll be good if you can volunteer, come forward. We'll be taking just 30 seconds or 40 seconds clipping of feedback of this for the entire 2 days program. We welcome you to please come from forward and rest can not disperse for lunch. Thank you. Thank you.
If you don't let them have their lunch, you won't get good feedback.
start giving a lot of things, how fast you can react and how to do. Everything is again taught from the basics. So that way, clearing your mind is very important. That's what our philosophers also say. It is very difficult to empty our brain from the thoughts and etc. It is same in the vacuum chamber. And vacuum chamber is the first chamber where all the seminar that has been going on since yesterday, all the phenomena are taking place in that chamber. Okay? It is that chamber what you see first, whether it is a display division or a seminar, seminar means semiconductor. Now of course we have to play, that's why it's called display today. And all these phenomena are impossible. It would not have been possible at all if there was no vacuum chamber. So this entire economy, that nanotechnology, basic electronics, which all took place only last 50-60 years. Before that there was no electronics even. There was no BTech ECE. It is only a mechanical, civil, electrical, that's all, physics, maths, chemistry. But only the last 60-70 years, thanks to great physicists like Bodin and great chemists, all these technologies came, and dynamics of electron, that's called electronics, has started, and that branch enjoyed like anything. Last 20 years, of course, computer programming has taken over. Now intelligence is no more required. Artificial intelligence is now coming up in a very big way, and if you don't know any language, machine language. Okay. So AML has come, and if you go back, the history lies, the root cause lies in vacuum. Whether it is a discovery of electron, whether it is a discovery of proton, or even atomic structure, entire quantum mechanics, most of the subjects, they are all started from a zero pressure. It is better to have low pressure, not very low, but 1 atmosphere below. So this is 1 atmosphere. I don't want to go to the slides because if I can cover everything in 5-10 minutes, so that I will not feel guilty that I have not covered this, that, etc. So if I cover everything, then whatever 1 hour, 1 hour, 20 minutes given to me, I can only play later. So vacuum is required for semiconductors. That's what people say. Vacuum is also required for display. But these are not the only game fields. Vacuum is much more wide. Okay. So electronics is required for certain operations. Something else is required for certain, but vacuum is required for everywhere: food processing, pharmaceuticals, metallurgy, nuclear engineering, space technology, and then electronics. Okay. So even the electrical engineering, the highest voltage, 110 kV type of thing, if you want to open, you have to have a vacuum interrupter. Otherwise, it will create a lightning almost. So every field, somewhere or other, you will see vacuum. And the electronics birth took place from vacuum diodes, vacuum triodes. For a long time it went on, and we were, our earlier vacuum specialists were very happy that vacuum technology was very strong and all. Suddenly semiconductor came. And semiconductor electronics is in a way against vacuum based electronics. There are no more vacuum diodes, triodes that we can see in the day-to-day world. But of course, if you go to large power, very high power, then you will have to go to BEL and purchase 1 kilowatt or 10 kilowatt type of triodes, etc. There semiconductors cannot match. Okay. So power diodes are there, but not to kilowatts or megawatts. So this is we started the game, and today I want to confine myself of application of vacuum in semiconductor. But before that, I want to tell you that vacuum technology is much more wide. Tomorrow, if you want to change your discipline, you want to do some agriculture, food processing or pharma, you have enough food, and again you will go through the vacuum technology. There it is medium vacuum, and that medium vacuum is 1 torr. But by that time, 99.9% of the air is removed already. 99.99% has been removed if you come to 1 millibar. 1000 millibar is our atmospheric pressure. 1000 millibar, same as 760 torr, same as 1 kg per centimeter square, same as 14.53
What is that? 14.53 psi. Good. 1 bar, 1000 millibar, 760 millimeters of mercury. Microns also you can multiply. There are some 8 to 9 units. Even after this formal course, I expect even in midnight if somebody asks you to say all the 6, 7 should be there with conversion formula. If you can do that, then you are eligible to enter into the first chamber of semiconductor manufacturing. Okay, that is where you have to peep through glass windows. You cannot go inside vacuum because you will not be oxygen. So it is very tough. Only Narad knows how to go in this deep space where there is no air molecules, but still he goes around. So it requires a different breathing altogether. So semiconductors, before I go to the production, measurement, system design, troubleshooting, application in 1.5 hours, which we normally take 1 semester course in our IITs. So I've been asked to do 1.5 hours, and in that I am already wasting my time and talking general things. So I know how the tension will come up slowly, but no tension, only attention. So vacuum technology is important for semiconductor. Why? People say something sucks, so high prep, that is a force concept due to vacuum. That is used in vacuum brakes in the trains. Okay. Vacuum is also used when you are taking cool drink against gravity. You are creating some 600, 700 torr, otherwise it will not go against gravity. And imagine you are in the first floor and you are giving a straw and a small cup is there, and if you can create vacuum, you can drink. You cannot, but Ramdev Baba can drink because he can create 200 torr by virtue of this expansion, P1 V1, P2 V2. So he knows how to do that. So it's all compression expansion. It is basically mechanical engineering. That's how most of the employees in applied materials are mechanical engineers. I was surprised when I went there. So I thought that it is all electronics and computer. There is no computer scientist at all there, but it is manufacturing of computer science, and it is totally mechanical, electrical, and little bit of electronics students. So there is a lot of things to do, and of course mother is physics and chemistry. So you should know a little bit about it. Today is the time for interdisciplinary research. There gone are those days, I am a physics professor, I am an electrical engineer, I am a mechanical. It's not possible. Materials are changing every day. And I don't know how Applied Material has rightly thought of that title, Applied Materials Company. Really, it is the materials which are controlling everything. Things are changing every day. Chemists, physics domains are closing completely. Physical chemistry, chemical physics, things are changing. As professor has told in the morning, I was really surprised to see so much of organic chemistry, which was called organic chemistry because it is related to organs, life. But today it is not. It is also, it's not organic chemistry, it is electronic chemistry. It is totally electronic chemistry now. Okay? Such long molecules, they thought that it can easily bend. The beauty of that is chemists could solve many problems which otherwise just by engineering we cannot solve. So these things are entering into different domains. So our domain is semiconductor manufacturing today. Tomorrow food processing, again I will talk vacuum in some other time. That is, a style is different. Okay, when you go to the semiconductor manufacturing, there are more than 150 processes. Anyway, 1.5 days is already over. I will not drag on this subject much. I will directly go to vacuum, which is not that much covered. Basically 150 front end and back end. By now you must know all these things. Front end means up to wafer fabrication, up to transistor, to be precise, up to transistor circuit. All that high tech is over, and that is possible only because of 10 power minus 8 torr. Then comes the back end, assembling, testing, and packaging and all. There also vacuum is required, medium vacuum. And so-called poor vacuum, medium vacuum, which we normally talk about in our vacuum cleaners in the morning hours. Then our coffee, which is a vacuum freeze-dried product. Then every second we are breathing 500 torr, that is also vacuum. All this we call it as poor vacuum. When we drink against gravity also, we don't think it is a vacuum. But 99.99% already has been removed. By the time you come to 10 torr, 10 torr is routinely used in food processing. Hindustan liver people know very well because their liver works much better than us. And they are doing 10 torr operations. If we enter into their companies, all are vacuum pumps. vacuum chambers. What they are doing? They are trying to evaporate water at room temperature. So, our concept is totally different. We think that 100 degrees it boils. No, 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 20 degrees itself it will evaporate totally. So, water immediately changes. Now, why I am telling this point now? That is the first enemy in semiconductor manufacturing. If you start creating vacuum, before you put PNP or NPN, whatever you want to make, you make VLSI design and go step by step according to that. The first step is to get a vacuum. If you do not get a vacuum, nothing starts. And by the time you come to 1 tar, already water vapor is evaporating, which was there initially when the chamber was cleaned by some workers, and they would have made some sweat like this. And 1 drop of sweat, 1 cc, 1 micron, 1.3 cc maybe, that at 10 power minus 8 are billion liters of billion volumetric liters, because at that pressure density is so small, billion liters of moisture will be there. That many liters you have to remove. Otherwise, what you are going to get is not at all an IC chip. It is not even potato chip. It is just a chip. Nobody bothers about it. Okay. But for your information, potato chips also use vacuum technology, because that is where, without spoiling the useful content of bacteria, etc., they try to dry it up. For them also, moisture is the enemy. For the Nescafe powder, moisture is the enemy. Semiconductor, moisture is the enemy. Fruit juice, squash, moisture is there. Everywhere moisture is the enemy. But we all want again moisture to be added so that we can drink water. So that is nature. Water everywhere, but you cannot apply it at all in high tech. But today's high tech is one thing more, hydrogen technology. All of you must be knowing by now, hydrogen technology. Hydrogen plus oxygen together is what God has created water already. But now all that we need to do is just to remove. If you can split hydrogen and oxygen in a cost effective manner, you are a trillionaire, billionaire already. You don't have to go to USA. I am telling you, if you can know, because we have enough water, ocean. And if you can remove salt from there, that's called vacuum evaporated salt. You will get regularly very good advertisements in TV. So that's where I always feel, oh, vacuum. And when you take coffee flask, that is also vacuum thermal insulation, mechanical engineering aspect. So everywhere vacuum is there. I have to tell because this lecture is on vacuum. But if it is another thing, I will have to tell accordingly. Okay, so what are these 150 steps? I am not an expert in this line at all, but definitely I know most of them require different levels of vacuum. First, the wafer has to be introduced, that poppered looking type of thing, 30 centimeters, that has to be introduced. That has nothing, it is only silicon, and it is made out of sand. Sand is silicon dioxide. Just like if you can split hydrogen and oxygen, you will get beautiful energy saving, no need to have petrol, anything. If you can split silicon dioxide, which is quartz, into oxygen and silicon, you can have oxygen lot, and Silicon Valley it becomes. Your Marina Beach becomes Silicon Valley. I am sure after 100 years a technology will come where most of these beaches can be converted into Silicon Valley, because 50% of the sand is silicon only. So as time passes, things are changing. Have we ever thought that one day will come where with all these things I can talk to my family anytime, and night and day I will talk? Okay, I never thought 20 years back. So if technologies can change, definitely after 30-40 years, silicon dioxide, our beaches will definitely become Silicon Valley. Okay. And similarly, our water, rivers, etc., they are the sources of hydrogen and oxygen. That is the power of chemistry. Morning I have seen from him the way he explained things. But little bit of physics now. This I don't have to tell you anything more than that. But I remind you, vacuum is required in semiconductor technology for two purposes. First purpose is contamination should be as small as possible, not as small, almost nil. Parts per million, even less than that. If you want to go to nano scale of pattern sizes, and capacitors are vertically grown, of course inductors are not there in the IC chip, but after some time they will also come very soon. And you are keeping hundreds of hybrid electronic components inside that small chip. Okay. So you can imagine the role of vacuum at this stage. You can take it for granted. Without vacuum, nothing goes on in semiconductor technology. So it is good enough if we little bit know about these things, because tomorrow when we get jobs, youngsters, they will not be asked to design very big circuit design, etc. and all. That is anyway there electronics people will do, or that also programs will do, you don't have to do. But you will be asked to handle the vacuum equipment. You will be asked to see whether vacuum has come or not. You should see whether measurement is accurate or not, whether it is 1000% error or 1% error. You are saying 10 power minus 3 tar, yes it has come, and start growing p-type. It never happens because it may be 1 tar, because gauge it has shown like this something short circuit and it is not working, typical gauges. So you should know some bit about production of vacuum, some bit about measurement and system design, how to design chambers, etc. to make your silicon films, and little bit about troubleshooting. If something goes wrong, you should know how to trouble the shoot the trouble. You should not trouble the shoot. Okay. Now problem comes in between design. That is where we are not that strong. We have to improve our design aspect. So a technology has got 5 components, any technology. First is production, you have to produce something, then measure it accurately. That accurate measurement somehow is not there. Most of the gauges that I have used for a long time, whether it is 1000 millibar or 50 millibar, it shows always same reading. Below 1 millibar, it starts waking up. Oh, I should say -1, -2. There are gauges like analog gauges manufactured. I don't want to name anybody, but the gauges are like that. So you do not know whether it is 100 millibar or millibar is same as star for your information. Just keep it for you. Which unit you like? I think let us use star word because he is a great scientist, Star Silly, who has spent all his lifetime only went up to the hill and then inverted everything. No other work he did. He just only inverted 76 centimeters of mercury into multiplied by 13.5, that much height of water column. So lots of experiments he did and he left. Nobody bothered. Later if people thought that this is vacuum, and it has been named after him, Star Silly. Most of the scientists, physicists, they have got their units after them, whether it is a Faraday or whether it is a Henry or whether anybody, ohm for example. Of course, it is not our ohm. Okay. So things have changed a lot. Now there are no more units. It is only making it better and better, cheaper and cheaper. That's so the technology now. We are not going to discover anything. We are not going to invent much. We are only trying to make the material smaller and smaller and smaller, faster and faster. 2 directions world is going. Speed is up, millisecond, microsecond. I don't have time. Oh, 1 hour you have to complete. 100 hours I will teach. No, not possible. Now similarly, no, still smaller, sir. I want to have a cell phone like this, and the collar ka beach somewhere. I don't want to have big things. Very small. Size is going down, down, down. Speed is going up and up. These are the 2 things. If you know how to do that, you are a master. So in all these things, whether it is a doping or a diffusion or ion implantation or source beamline or a PVD or a CVD or LPCVD or plasma CVD, plasma is also a vacuum phenomenon. So nothing works without vacuum. I have put somewhere here and there. These slides will be given to you. So don't worry about taking any photograph or any of these things. Slides will be there, and I have given lecture on NPTEL, SWAYAM NPTEL, 60 lectures are there. You can go through slowly at your leisure. That will be 40 hours things, which I will cover in 1 hour now. Already 20 minutes are over, but I have still in the first slide. But I want you to understand this first. Forget about pumps and all. You are not going to make a pump. You are not going to make a gauge. There are companies who are there and they will be happy to sell you, and they know how to teach about gauge, etc. much better than all of us. Okay. So don't worry about production, measurement, etc. You worry about basic concepts, system design and troubleshooting, because trouble you have to shout in your place. There will be nobody. If you ask company people to come, they will say $500 per day. You can shoot it in 5 rupees if you know how to do that. Okay. Please keep that in mind. So this later also you can understand this. This is a typical fab. See, all this is because most of these things are called tools in the semiconductor language, but actually they are nothing but some plastic boxes inside, lots of vacuum pumps, chambers, couplings, walls, and feed throughs, optical things, electrical supplies, electronic things, varieties of moving things, all these things. This is basically a clean room. Nothing is clean actually. It is only 10 clean room, 100 clean room like that, parts per that molecular density. It is not air molecules. Clean room does not mean it is air free. It is only a particulate contamination, because one particle is good enough to spoil your p-type into n-type. So you should be very careful in this contamination problem. That's where vacuum is required. I was telling two purposes. You must be wondering, this fellow has shifted already from that dialogue. No, I am coming to that. Second point of vacuum requirement is, when you want to deposit something, you want to give, according to Newton's first law, if you do something, you should go in the same direction without hitting with anybody. Then only it will, you can predict where it is exactly going, where it is exactly depositing. After all, what is PVD? You have to evaporate, melt and evaporate. Physical vapor deposition. It is not vapor actually in the vacuum. They are molecules. If you put an agarbatti, if you take it, and that is called vapor. That is physical vapor deposition. If people don't want to understand class 1 to class 2 boys, you can tell them physical vapor deposition is this agarbatti. Temperature is very hot, it is melting and evaporating. And what is sputtering? Sputtering is nothing but whenever you go to temple, Shiva Mandir and all, you will say and you scratch it and put it. This is a thin film. Okay? That is exactly that we can scratch like this because this is in micron. And that is also fine dust. In fact, this nanotechnology was discovered long back in Bhasma. That's why the capacity of those drugs are very high, because all 360 directions it can attack the thing, which is going on now in the advanced laboratories, even in this institute, okay, because nano powders. So, okay, point is, it has to go in the straight line. Why should it go in the straight line? Somebody is hitting. Right now here in this room, every cubic centimeter contains how many molecules roughly? Cubic centimeter, like a die that we play now. That contains 2.5 into 10 to the power of 19 molecules. Billion molecules are there every cubic centimeter, and you can imagine in this room. So all of you can write down if you have some pen and paper. Later you can send it to my net. How many molecules are there in this classroom? Containing some 8 meters by 12 meters by 3 meters. You will be surprised, and if you collect all those molecules and weigh it, you will think it is milligrams, but it will be more than 20 kilograms. Okay. So, very surprising figures will come in vacuum. 2.5 into 10 to the power of 19 molecule, nobody bothers, we are regularly breathing. But when you want to go to semiconductor-based manufacturing, you have to reduce it to at least 10 power 9 molecules. We are not making anything empty. Ultra high vacuum molecular beam epitaxy meant for nanoscale techniques, for highest level of IC chips. There also the chamber contains 10 to the power of 9 molecules per cubic centimeter. Nothing is free. If you go to the deep space near the interstellar spaces, there also 30,000 molecules are there, which is 10 power minus 12 minus 15, which is impossible to create on Earth. The day you create 10 power minus 12 tar on Earth, your IC chip quality will be 10 times better, because your quality control will be very high. But we are now doing maximum up to 10 power minus 8, 10 power minus 9 maximum, because who will create vacuum? Pump manufacturers slowly come up. There is a step-by-step improvement in the vacuum. And what is being manufactured by pump manufacturers, that somebody should measure it. So measurement is also very difficult. How do you measure 10 power minus 9? Somebody says 10 power minus 9, you remember, that's all. No, you have to exactly figure it out. Who tells this? Somebody has to tell. Boyle has told PV is equal to nRT, and that is valid only under vacuum conditions. It is not valid under high pressures, because Van der Waal has made some plus A by V square into V minus B. That is valid here right now. PV is equal to nRT is ideally valid in vacuum. So we are all ideal people if we ever switch on vacuum pump. I am telling you, because the dimension of the molecule with respect to the distance it travels is much less. So entire volume is freely available. So the PV is equal to nRT is valid, but otherwise it is not valid. So, all these basic concepts he wanted me to explain. So, I started changing my style. So, that is why I am telling all this. And this clean room contains some such things. With respect to particle contamination, it is very pure, it is very clean, but it has contains oxygen, nitrogen, etc. Okay. Oxygen, nitrogen with all this inside, later I will show you later some vacuum pumps, etc. But if you go inside, what this fellow will be doing inside, they are all vacuum chambers, ultra high vacuum tight flanges with the gold gaskets and very nice looking flanges, shiny surfaces, etc. And these molecules should not go inside. Then again silicon dioxide se silicon banaya, now again silicon becomes silicon dioxide. We want silicon to be pure silicon, we intentionally impurify with p type or n type, whether it is boron or phosphorus, then only we create PN junction and 2 junctions transistor or IGBTs, etc. Then try to do these IV characteristics, all that finally technology will come. But if oxygen goes into this chamber when we are heating the silicon, we are insulators, it is no more semiconductor. Okay. So, vacuum is very important in metallization, in thin film deposition, in plasma etching, ion beam etching, sputtering, call it every aspect, even the introduction of the that wafer, that itself requires a force. So, all that pneumatic arrangements are also vacuum. Vacuum creates the mechanical effects, vacuum creates evaporation effects, vacuum creates very clean ion beam to travel straight line, and otherwise it is not called ion beam, it is ion cloud. Okay. So, you have to think in this direction, then when you enter into our laboratory, you start feeling the importance of vacuum. So, which I have already covered this, PV is equal to nRT. So, if you take P as the 0.1 megapascal, which is atmospheric pressure, and R is standard, T is the room temperature. If you calculate and do all that little bit of simplification, because you will get PV is equal to nRT is for moles, but you have to multiply with Avogadro number. Then you will get real number of molecules, oxygen molecules. That will be this much. So, somebody must have been thinking, how did he say that 2.5 into 10 to the power of 19? Has he seen? Suppose I ask you to count 2.5 into 10 to the power of 19 molecules, your lifetime is not enough. But scientists know how to do that because they use scientific principles. Avogadro know already 6.023 into 10 to the power of 2. How did he tell? This is a very interesting story. Some other time if you call me, I will tell, not now. Okay, because that will be 2 hours. Now, this is my atmospheric pressure. Below, this is my absolute emptiness, which is impossible in the world or universe also. Nowhere it is there. Absolute zero is not there. There is nothing called negative pressure. Sometimes in the refrigeration industry, you will see negative cycle, negative, with respect to atmosphere. That is called gauge pressure. So, we are bothered about absolute pressure in vacuum technology. Don't go for gauge pressures anytime, very dangerous. There is nothing called negative pressure, force per unit area. Same pressure is related to molecular density in 1/3 MnC square bar. Same is related to F by A for force per unit area. And same pressure is also related to N into K into D in terms of thermal energy. P is equal to NKT, P is 1/3 MnC square bar, P is F by A. You can say anything. Everything has got its own beautiful physics behind it. And they have done all these things. So, what is important for us is below 1013 millibar, we have to go several, this is a log scale, okay. We can go up to this 0, 10 power minus 13 minus 8 here. And above 10 atmospheres, 100 atmospheres, 1000, you can go anywhere. So, above atmosphere, there are so much of range of pressures, but no application. Only few applications, high pressure technology, little high pressure chambers or steam coffee or something, that's all. Whereas, low pressure below 1 atmosphere, how much you can go? Maximum only 1 atmosphere. Above 1 atmosphere, you can go to 1000, no applications. Here, railway brakes, and then your Kisan squash, Nescafe powder, vacuum cleaners, all these things will be over here. And by that time, you have already removed 99.9% of the molecules with respect to this. But no application has started, no electronics BTech, no metallurgy BTech, no electrical even, not many things are most of the electrical things, whether tube light or all these things are all vacuum. First you remove the air, fill it with something, then only you will get light. Is it not? Even copper manufacturing, otherwise it will be copper oxide. So you cannot get anything without vacuum, even in metallurgy or electrical. Space nuclear, definitely not possible. ISRO will be closed unless you cannot maintain vacuum below 10 power minus 6 star. BARC can never even open one small accelerating of proton unless you go 10 power minus 10 tar. So such a small range 0 to 1, we have umpteen number of applications which are all high tech. It's not B-tech, M-tech, it is high tech. Okay. So routine technologies that we see in day-to-day life are higher pressures, like maximum 2 atmosphere, 10 atmosphere, medium pressure. These are all small scale. When you want to understand vacuum technology and associated semiconductor and display, you have to talk about molecules. You cannot talk about gas. Gas trouble is over. Okay, it is no more gas. Fluid mechanics book can be closed because it's no more fluid. They are molecules. They don't depend on P2 minus P1 air. There is no force. If suppose 10 power minus 6 star is created here, there can be a molecule here, it does not understand there is a 10 power minus 9 here. Because how does it know? The distance between the free molecular distance, that is called mean free path, is kilometers. The chamber dimension is only at 4 meters maximum, let us say. That 4 meter, that whatever he wanted to lift, morning he was telling, no, 4 by 4 glass plate, maximum 10 meters. Whereas 10 power minus 9 tar, the mean free path is more than 10 kilometers. So every molecule will travel freely 10 kilometers before hitting another molecule. So there is no question of there is a pressure drop, I will have to go against pressure drop. No, I do not know whether there is a pressure drop. I am independent. The flow is no more pressure driven flow. It is now more viscous drag. It is totally molecular flow. It can be calculated by Monte Carlo techniques. It can be calculated by statistical variations. It is nothing to do with the routine things. You have to know that. Because when you go to ultra high vacuum design systems, people have to do all these technology. How much is the molecular flux of a gallium and what is the arsenic coming? For every 1 gallium atom, 1 arsenic should come. If 1 atom and 3 atoms of arsenic comes, you will not get your gallium arsenide semiconductor wideband. Okay. So what we think apparently looks normal, they are extremely perfectly done under ultra high vacuum. That is because technology has developed to such a level that people know with optical technology, electronic technology, materials technology, high vacuum technology, plasma technology, and varieties of things, electromagnetic principles. Many things have evolved over a period of 100 years. Today we are able to control at atomic scale. That's why vacuum is the mother for the invention of electron, proton and atom. Every picture is alpha particles. Everything was discovered after creating vacuum. The first discharge tube, for example, this 1 tar, 10 tar only. So highest, if you make a high voltage here, you will get some small charge. Unless you go to 10 kV, professor knows CPR professor is here only, and they know 33 kV, 100 kV, nothing happens. Whereas if you put 33 kV in a vacuum, you will get immediately spark, arc, etc. If it is a small amount of microampere, that is called discharge. Little more, it will be a spark. Little more, it is called arc. If it is still more, then it is called lightning. So basically everything is a discharge phenomena, and discharge is coupled with recombination. So if you don't make it combined, that is called plasma. That means it is coexisting. Electrons and protons together are able to coexist. That is called fourth state of matter. And the temperature equivalent of that is million degrees, which is used in nuclear fusion. That is again 10 power minus 9 tar. If that is not there, we cannot create artificial sun on Earth, for which billions of dollars is being spent in International Thermonuclear Experimental Reactor. Every country has got their own nuclear programs, and nothing would have been possible. But the costliest experiment ever done in the world is called LHC, Large Hadron Collider, to get the God particle. Two molecules have to hit head-on collision, 10 power 19 molecules, and with so much of velocity when you do, you will create the Big Bang. And that experiment, 7-8 countries together have to do it. 27 kilometers ring of vacuum has to be created underground with so much of superconducting magnets. Very costly experiment. Finally what? Two molecules are colliding with each other. How does it matter for us? No, it matters. Is it not? So the technology is like that, and it is intricately related to vacuum. Okay. Now coming to mechanical engineering, in a compressor we take suction as the atmosphere, like when you go to for a tire filling the pressure of your car, etc. Suction is from air. Air is freely available, that's why you take. Otherwise, after some time, air is also not available. If you go to Delhi, you get lot of dust freely. Okay, so no, that is a index. Measurement of index, of your lifestyle is now, it is called what? Air purity index. It has come now. How much of molecules are there? Now, in that we have to create clean room. Okay, so first we have to clean ourselves. And that's why people are not allowed to go inside. We don't know from where you have come. So people have to take shower bath, enter clean room. There, if some other time, if he arranges only clean room seminar, we will talk about that. Very beautiful explanations are there. Of course, in Google also gives a lot of information. But if you meet and talk, it will be much better. So compressor sucks from atmosphere and fits it to a medium pressure tank at 10 atmospheres, 100 atmospheres, depending on that. Our Indian gas is 10 atmospheres. Our argon gas is 100 atmospheres. It depends on the vessel design and all mechanical engineering. Lot of work is going on there. We have to design that also for negative, not negative, lower than the pressure. That will be reverse. If you take a bottle of this one, I can do 2-3 vacuum experiments. So if the teachers are here, when they go back, you can do some 200 rupee experiments easily and create some UGC journal publication easily. So what all that you need to do is reduce little bit of 20 tar, water evaporates, phase diagram, measure PT, etc. properly, explain something, and you say that physics education journal, you will get publication. Second thing is, if you put, there are lots of things, designs. Why these are reinforcement. Like this water bottle. Under vacuum, it will collapse. So if you don't want it to collapse, you have to give stiffener rings. So these are all mechanical engineers know much better than me. But why I am telling now is, when you make vacuum chambers, you will have to do it. If you are an intelligent mechanical engineer or metallurgical engineer, you should do it with 0.3 millimeter thickness. If you purchase a Korean steel, which is very costly, okay, right now, very good stainless steel is also not being manufactured here. So our now only manufacturing things have taken over. See, even if you see the nail cutter, you will see made in Korea. Okay, and because such a high, I purchased a long back when I was doing my almost PhD. Even though it is shiny, so that is called metallurgy, because that is vacuum metallurgy. Okay, but stainless steel, if it is not there, very good copper, OFSC copper, not possible. Okay, OFSC flanges, we cannot make anything in India right now, but we know how to put the thappa made in India. Okay, that stamp is working very nicely, but we have to do it. We have to do. This is the time, and they are doing a lot of service by organizing such things. So in vacuum, what they do? The exhaust is atmosphere. The suction is the chamber to be evacuated. This is UHV chamber for molecular beam epitaxy, for making gallium arsenide device, for making IR detector. That is the whole theme. Now everything has to go into this chamber of commerce. Okay, this chamber has to be evacuated. This is called process. In compressor, process comes here. In the vacuum, it comes here. In semiconductor manufacturing, by chance, if you want to dedicate yourself to semiconductor and display, you will have to do this only. And after getting vacuum, then you do something inside. If you don't get vacuum, you don't have to do anything. You can go on leave. Okay. So this, please go through it little later at your leisure. You have these slides. So already I told you, human beings can create 720 tar by breathing, and somebody says, I don't know vacuum, sir, you are talking something, I better go. But every minute, if you stop creating vacuum in your lungs, you don't have to go. For 4 people have to come. Okay. So, and if you don't know how to create 400 tar by mouth, if by chance your lip seals are not good, you cannot drink. You have to be like an old man like me, drink against gravity, use the gravity principle to drink. That's why most of the old people, they give glass fruit juice. They cannot drink through a straw. But you people can drink through even 4 straws in one bottle. Okay. So this straw, how it works? Because you are able to create here inside 600 tar, okay, or 700 tar, depending on your capacity. Of course, Ramdev Baba can 3rd floor se bhi he can drink. We cannot do that. If you go to Everest, Mount Everest, it is 300 tar. You know that? And 60, 70 degrees water evaporates. So now hot summers, 50, 60 is nothing nowadays. Okay. So, and desalination plants you can create at your home. Just to bring it, put solar energy, 50, 60 degrees, get some 100 tar, 20 tar, which is easily available by any vacuum cleaner. Just replace the thing in such a way with a metal thing. You will get beautiful salt, evaporated Tata salt right at home. I am telling you. But they have done it in a stylish manner. We cannot do that. That's all the matter. And if you want to create a Pirani gas, you come to me with a safety pin and a good old broken bulb ka filament, and put it with araldite, one plastic rubber bottle or something which you are broken at this Amrutanjan bottle, keep it, and then I can make you Pirani gas. We have made it one BTech project. He got best project award. Okay, he made a Pirani gas and compared with the Pirani gas manufactured by so X and Y. And it works same because it's a thermal conduction, heat transfer in the convective heat transfer or residual gas conduction. We produce the vacuum and hot filament. Filament is, where do you get? I don't have money. So what to do? Go to the bulb and break it. My wife shouted, why are you breaking this bulb? I said, government of India does not want incandescent bulbs. That's why I am breaking. Okay. That one you keep it in the shot with a safety pin and structure it, because safety pin has got a beautiful loop and all. You can easily attach and put it in a nice hot wear anemometer type and put it in an araldite. If nothing is there or some gum or something, you put it and then put it into a vacuum chamber. You will get immediately resistance multimeter will measure exactly, it will come 10 power minus 1 tar that much. In fact, it comes much faster compared to some of the gauges which normally never come, they sleep. So it worked, and we produced one BTech thesis out of it, 250 rupees. Pumps manufacturing is little difficult. If you are a good mechanical engineer, you can make that also. That's not a problem, but little difficult. Troubleshooting is everybody's game. Today, if you go to any motor or repair, etc., the fellow knows much more electromagnetism than an electrical BTech or anything. If you say this theta direction current goes, z direction field comes, and then r direction force will be there, this is Lorentz force, all that, he does not know. Sir, you repair it? No, sir, you have to hold it like this, do it like this, and do it like this, and put it, and it will work. So that is called troubleshooting. In vacuum technology troubleshooting is also high tech, because you need to have mass spectrometric deflection magnetometer, MSLD. It is a very big word, and if you don't use that, you will end up in 10 power minus 5 tar. And if you don't get 10 power minus 9 tar, your boss will say, don't switch on, don't go to the PVD or CVD or anything. Your CV will be out. Okay. So you have to produce vacuum first, then only come to me. Then what to do? Some intelligent engineers, minus 5 ko thoda gain factor, they are electronic engineers, some parameter, something with a screwdriver, they can show minus 9. And it will, by chance, if the device goes somewhere, Korea or somewhere, they will say that it is no more transistor, it is some other sister. Okay. So forget about it. So you have to be very careful when you want to produce ultra high vacuum, without which no semiconductor can ever take place. Even metals also. Metal also become oxide. Every fellow wants to become oxide, because oxide means happy. You are dull. You are a ceramic. Okay. And maximum what happens? You can take coffee in that. That's all. Ceramic, nothing happens. It is highly non-reactive. So everything becomes oxidized as time passes. If hydrogen became oxidized to become water, silicon becomes silicon dioxide to become beach. So like that. We also have to get oxidized someday or other. Okay. Now, when you go to the higher altitudes, as you go up and up and up, vacuum level changes. And after 10 kilometers, it is already 76 star, and another 10 kilometers it is 7.6 star roughly. So you can say for every 10 kilometer one order has gone. So if you go to some 30-40 kilometers, you don't have to purchase Hindevac rotary pump. 10 power minus 2 tar is available in infinite volume. You just do all your experiments and come back, but you will not be there to come back because you need oxygen. But your system will work very nicely if you go on the window, whatever is there now. If you break open the window of a aeroplane at 10 kilometers height, what will happen? You will think that it will rush like a car. Whenever you open a door, no, when driver sneezes or something, you try to open something. No? If you do that, air comes inside, but here air goes outside. And I have done one experiment with, not experiment, I have done one calculation and earned some 20,000 rupees by calculating time for death. If window is broken by chance in a aeroflight, it moving at 8.5 kilometers height, what is the time for which all the blood will come out? Because it comes out in few seconds, not even 1 second. It just comes out because outside at 76 star here suddenly. 760 star inside originally. So good enough across all the membranes. Cell walls will rupture like anything. So this is where the forces, enormous forces are naturally realized by just removing the air, that we are using it every day by cleaning vacuum cleaners. And 99% of the dust is removed by broom. That fellow is only 10 rupees. This 0.1% dust which you cannot remove, but you want very nice looking things, etc., that requires 10,000 rupees. So it is the fineness of the cleaning that is costlier. Same thing in semiconductor chip manufacturing. It is the parts per million impurities. If you do not do that, your doping is also parts per million, and you are already doped. It is impurity. One monolayer of oxide will be formed in microsecond. What do you observe in the nice research scholars working in the biotechnology, trying to see the enzyme structure, etc. and all? Before they see, already it is not original structure. It is already monolayers are formed. So they have to do it under high vacuum, scanning electron microscopy. Some fellow will scan it. You cannot scan easily because you require other things. So even to see the objects properly, interfaces, surfaces with a beautiful publications in physical review, you have to do that under vacuum. Otherwise, you cannot create structural analysis. XRD, for example, unless there is a 10 power minus 7 tar, the electron will not travel up to the copper target, hit and produce X-ray. It will be mixed immediately, and copper will be oxidized. It is no more pure copper. So it requires 10 power minus 7 tar sealed forever for 10 years. So that technology, that troubleshooting is, it is not only important to produce minus 7 tar, but leave it at that situation for 10 years. Vacuum interrupter, it is not only important to produce 10 power minus 8 tar, but leave it in the high voltage lines for 20 years for a fault to come anytime. So it is a safety requirement. So there the vacuum technology takes a different role altogether. There it is sealed tubes, TV tubes for example, they are all sealed tubes. Vacuum level is not much, 10 power minus 5 tar, minus 6 tar, but it has to maintain that minus 6 tar for 10 years. Who will do that? First of all, leak should be reduced. Second is there should be some local pumps like getters, which will take some action. As and when little bit pressure rises, it can take care. So all this is a technology that is called ion pumping technology. So why I am talking all this is I can avoid the things. Other things you can easily go through. Why rotary pump works? That is just to go to any industry, you can get much more experience than listening to my lecture. Diffusion pump, you are not using it in semiconductor manufacturing. But olden days it is used. Nowadays it is turbomolecular pump only. Cryo pumps, if you are very rich and all, you can purchase that also for certain devices. Most of the time, rotary pump and turbo pump. And if you want huge pumping speed for few minutes, like initially that is called the wafer letting into the thing. That is one chamber. What is the popular name? The loading in chamber, quick loading chamber. That chamber will be, because every minute there will be 2-3 wafers have to be sent, very high speed. Otherwise, the 130 crore cell phones cannot be made. So you require a lot of things, and each person requires 2 phones. Okay. So that's how it is. So at 10,000 kilometers, we have 10 to the power of minus 10, 13 tar, which is naturally available, on which semiconductor manufacturing can be done without any conferences, without any seminars, freely. You put silicon oxide, everything you can do with your hands. No glove box is required. 10 power minus 13 tar is there. So that is where after 100 years, maybe such things will happen. We do not know. 100 years back, nobody thought that there will be a cell phone like this and all. People will, cell means it's a dangerous, it's a jail. Now cell means it is with us only. Okay. So this you read it at your level. What I wanted to understand is nature is very powerful. That's why the highest impact factor journal is Nature journal. Morning professor had one paper in the Nature journal. It is 32 impact factor. Okay. So what we cannot do, nature can do. We think oxygen, nitrogen molecules here, but in nature we have nascent oxygen, only O. O3 also is there, O is also there, O2 is also there. Different fellows are doing different things. And the entire periodic table, the first fellow, head of the department, H, that fellow is the main fellow. Now you people are asking for that only. And 2H together joining, creating an alpha particle under high vacuum conditions will produce sun. And if you can produce even 1 crore of that sun here, each entire Bangalore can be getting power for hundreds of years without any nuclear or anything. That's called nuclear fusion. That is possible because of vacuum technology. So every aspect of life, someday or other, somewhere or other, whether it is a morning coffee or a breathing or a simple vacuum cleaners or a TV that we are watching, that is LCD, LED, all these are there. And then whatever goes when you go to hospitality. So there we will get MRI, that is cryogenic container. First container is vacuum. Without vacuum, cryogenics cannot stabilize. Without cryogenics, superconducting magnet cannot be there. Without superconducting magnet, our biological hydrogen, again hydrogen, will not react to produce that proper relaxation, and that is called magnetic resonance imaging. Everything is possible because the first box is vacuum, and that is thermal vacuum. Whereas in ionization and other places it is called ion vacuum. In your case, particle contamination vacuum, because the ion beams have to travel. Ion beam should not be neutralized. And fluxes, when you are evaporating silicon or whatever it is, it becomes atoms and they will go like a bullets. So that's why by electric and magnetic fields you can produce torchlight type beams. They are called molecular beams. When you do it at a slow pace, one monolayer will take 10 hours in 10 power minus 13 tar. It takes 10 microseconds at atmospheric pressure. So here one monolayer is formed as an impurity layer. Same thing we are trying to do in a controlled manner at 10 power minus 12 tar by producing a flux beam with cos theta, sin theta, all mass work there, because particles are moving in a straight line beam and molecular beams are created, ion beams are created. Otherwise you will not have even cathode ray oscilloscope. A cathode has to form as a ray, otherwise it will be electron cloud, is it not? So these are the fundamentals which already you know, but I just want you to know again what you know already. Nothing more is required. If you want to be in semiconductor business, if you are very careful, if you are very good in clean technologies, clean rooms and vacuum, there is nothing very easily. If Korean can make, Taiwan can make, India can easily make. It is not a difficult thing. It looks like a very difficult technology. It is not. Somehow we have not started. Now we have to start. Please start. And start from vacuum, start from producing silicon, silicon popped at least, that we cannot make. Silicon beam, a silicon pure crystal we cannot make. So where will you dope again? So you purchase silicon crystal from one country, purchase ion beam from some other country, purchase a vacuum pumps from some other country, purchase X-rays, purchase neutron beams, everything from all countries and put make in India. Okay? So we'll have to be careful. Unless we do like this, when 129.99 crore people do not know what is electronics, and we simply say by just few institutes can create technology. But I am not talking negative, we have to create. And do see to that it penetrates. That's where educational institutes and societies matter a lot. And you young people, particularly teachers are there now. So you try to do a low cost experiments, whether it is required or not, whether students want or not. Please show the practical aspects. Otherwise, if a third world war comes, governments say, all governments say, we will not give you cell phones. No, all the big companies, I don't want to name, and they are not there. And one full year we have to be there without cell phones till the war is closed. That's the way people are now, government, everybody says let us pick, because wars are now no more wars, they are star wars. There is nothing called missile, anti-missile. These are all laser beams. With a laser beam you can cover. That is because you have created a vacuum technology, lasers are created. So this is a high-tech event, no more B-tech. This is vacuum. I don't know what happened. What happened? Something. Okay. So next fundamental is molecular density, mean free path, and time to form monolayer. These three aspects if you understand, I am sure you will get minimum 2 lakh rupees salary. I am telling you. All that you need to do is, what is mean free path? It is not the distance between two molecules. If you are all organized people, no problem, where distance between is only 1 meter. But if I am asking you to go in random motion, you can travel in this room which is having only 4 meter, but you can travel 4 kilometers without hitting anybody. By the time you come here, this fellow will go there. This is called random motion. The second name given to the random motion is called pressure. That's why pressure P is equal to 1/3 mn c square bar. The c square bar is root mean square velocity, mean square. It is not linear velocity. Okay. So it is velocity of these molecules here right now, molecules 2.5 10 to the power of 19 per unit volume. They are moving with a velocity of 400 meters per second, half a kilometer. It will go to Delhi in after 2 minutes. But it's not going, air is here only. Why? But we all know that the velocity of these molecules is, sound velocity is 330 meters. Okay? And if it is hydrogen, it is 1 kilometer per second, because 1/2 mv square is equal to 3/2 kT, and for the same T, V will be high if m molecular weight is low. So that way, hydrogen has got more than 1.2 kilometer per second it can travel. Right now it is traveling here, but because they are traveling randomly, every micron it is reverting back. So it is, that is called Brownian motion in a way, or molecular collision in a way. But when it is moving so much, they are slowly creating a ensemble of gas. That's how molecules started behaving like a gas. Then molecular laws have become gas laws, like this theory, that theory, Boyle's law, Charles' law and all. Okay. Originally their molecules don't listen to anybody. Molecule only. Molecular flow. Ultra high vacuum, you have to deal with molecular flow only. So why I am telling all these elementary things are, because the moment you want to make one IC chip, even potato chip also require a lot of careful this one, otherwise it will not be sold. You have to have 10 power minus 9 tar, where the molecular mean free path is more than the dimensions of the chamber. So most of the time molecules will not impurify with anybody, because they have no time. It is freely moving. It will go up to here to the wall and hits. It is really wandering up to the wall. That is called van der Waal. It goes up to that and comes back. But nobody matters. Nobody interacts. Highly non-interactive phenomena. In physics, people know how to handle that statistical mechanics in non-interacting particles, etc. It's a lot of physics is there. Statistical. The vacuum technology is related to statistical physics, whereas the high pressure physics is all related to differential equations with all these Stokes law, Navier-Stokes equations, and fluid mechanics, Gauss law, all these laws are over. The moment you cross 10 power minus 2 tar, fluid mechanics book can be closed. CFD is not there. So all that softwares can be removed. If you want to go up to 10 tar, still CFD is there. But we look at 10 power minus 2 tar, it is totally molecular physics, molecular chemistry. And for that, if you want to do, Monte Carlo techniques have to be done, statistical calculations have to be done. It requires quantum computers to compute billions of events to take place. You cannot compute it with normal things. So how much flux, how much impurity has been doped. Once it is doped, it is diffusing inside. In solid, it diffuses. But in gas, it only transports. But it is not gas, it is a molecular ensemble. Molecules are there. So the flow of molecules is given by the molecular pumps. So I have given here, that is called mean free path. The average distance that it covers between two collisions is called the mean free path. It is not the distance between the molecule. Distance between the molecule right here is 5 micron. But average molecular flow can be little higher. And when you go to high vacuum, maximum distance between the molecule can be the dimension of the chamber, because they have not gone out. But actually, mean free path is 1 million times more than that, because that molecule, it is between successive collisions of their own, not with the wall. With the wall means it is the diameter, hydraulic diameter, but with respect to themselves means that is called mean free path. So that's concept I want you to make it very clear. These are all explained with lot more mathematics in books, kinetic theory of gases. Then mean free path you have understood. Molecular density is very simple. Density is proportional to pressure. P is equal to nkt. K is the Boltzmann constant. T is temperature constant. P is proportional to n. So number of moles per unit volume is anyway proportional to pressure. So you don't have to. You can measure the pressure by the molecular density. That is called Penning gauge does. Penning has understood that. He has made it proportional to n. He made some correlations and made a Penning gauge out of it. Heat transfer. If you are very hot here, when fan is on, it is cool. Not that heat flux has changed, because it is displacing and convective currents are there. Some other cold fellows are also taking this heat. So if you create that surrounding body as the room temperature and the central body is hot and create a vacuum, that is called molecular conduction. It is not conduction, convection, radiation, heat transfer. There is a fourth law that is called molecular conduction. Normally gas molecules convect. That's called convection, means currents, but as conduction also they do, but normally we think conduction means solid, but molecular conduction is there, because each molecule takes the heat from the hot filament of the Pirani gas, goes to the wall and stops, and it cools there. That is a hot body, hot sink, which is at room temperature. So this heat transfer will be poor if you go to higher vacuum, because number of soldiers are less now. So immediately what will happen? The central temperature will go up. The temperature, if you measure with thermocouple, that is called Pirani gauge. Instead of temperature with thermocouple, you put it in a Wheatstone bridge, and because the temperature of the filament gives you different resistance, that resistance is connected very accurately in the Pirani gauge. All that they do in a circuit, and the entire thing can be done in 1000. Since you do not know, they will sell it for 40,000. Okay? So it is nothing but the conduction heat transfer of the molecules and the temperature measurement indirectly by a resistance variation, thoroughly measured, accurately measured by a Wheatstone bridge, which is 100 years old. So that is called measurement. Production means what? You suck. How do you suck? You put the volume increase. If you increase the volume, number of molecules are same, then what will happen? P1 V1, P2 V2, because for the same n. If n changes, the things will be different. If the same number of passengers, suddenly bus volume has increased, you will become more aram. Okay? So pressure will be reduced. So compression expansion is the principle of production. Heat transfer and ionization is the principle of measurement. Troubleshooting is the molecules not to enter. Instead of molecules entering, you put some helium to enter, because helium can enter through fine leaks. So because smaller particle, and make the pressure gauge as the partial pressure gauge, not the total pressure gauge. Normally it shows 0. Under helium going inside by virtue of leak, it will immediately show a signal. So that is the principle of troubleshooting. So pressure measurement, troubleshooting and system design are all physical principles. Thermal conduction and P1 V1, P2 V2, ionization potential, ionization cross section, and electron production by field emission, and electron production by the thermionic. These are all the standard concepts which you all learnt in 12th class. They are again used in a high-tech level, and without which semiconductors cannot be made. So this table gives you that feeling of it. If you carefully observe the table at your leisure, you will understand. You will get time to form monolayer in nanoseconds. Already monolayer are sleeping. Okay. So now electronics semiconductor is also like that. It is a beautiful electronics field, and if you can think properly, you can do lot of research. What is research? You search again and again, research. That's all. You do it, you will get lots of papers. If I can produce 140 papers in 20 years, why can't you produce? My grades are very small in 10th class. Okay. So with that, if 760 to 0.5 tar, 0.5 to 10 power minus 2 tar, these are popularly known as low vacuum. Nobody uses in semiconductor technology, but we use it regularly in our household cleaning. We use it for our Nescafe powder. Nescafe juice is made and evaporated under vacuum. So, moisture is totally removed, fine particles are there, they are highly hygroscopic. That is why if you forget to close the lid, immediately it becomes a paste. Okay. So, that is how dried, that is called freeze dried products. Freeze drying is done and vacuum drying is done with all the electrical chokes, electrical transformers, everything after making impregnating to overcome the Lorentz forces. That impregnated rocky structure is degassed under vacuum because moisture is an enemy. That is why in rainy season transformer shorts, is it not? So, all this vacuum technology in electrical, pharmaceutical, all this, it creates much more jobs. If you decide not to do semiconductor, you still will have a lot of jobs with vacuum. Okay. But if you want to do semiconductor, you have to enter into high vacuum and at times ultra high vacuum. Ultra high vacuum is very difficult. Okay. Even few small micron type of gap between the two flanges, even with metal gasket, it will go inside, and instead of depositing your flux of impurifying p-type impurities, already oxygen has impurified. So, it has become already a field effect transistor, an impurity effect transistor. Okay. So, you have to be very careful in making. So, that much is the fundamentals, I think, and the rest is only for you to imagine. This is a rotary vane pump. I can do it very fast, but I do not want to do fast, nor I want to do slow. So, I leave it to you. It is a rotor eccentrically situated in a stator with a diametrically slot, and two vanes are kept. I should not use so fast because it is as good as not teaching. A rotor in a stator eccentrically situated with a slot. It does not become two pieces. Slot is only some distance, end it is solid piece only, otherwise it becomes two pieces. Okay. And these vanes will keep on rotating because motor is connected here. And when you do that, you will create such structure, A vane, B vane. This will come this way, that way. So, this is connected to my chamber, semiconductor manufacturing chamber. You have to start from 760 tar. You cannot get just like that -8 tar, turbo pumps, etc. First, you have to start from atmosphere only. No matter whatever intelligence you are having, you have to go to LKG first. Okay. So, you have to do this. So, when this starts rotating, this volume, this moon-like structure volume is added to the original volume, but the number of molecules are not same because it is not giving any more molecules. So, P1 V1 760 tar into 1 meter cube has brought into 759.9 tar into 1.01 meter cube, because this much 100 cc of volume is added to that by virtue of rotation. Why it is eccentric? If it is eccentric, you will have three points in a coordinate system, in touch points between two cylinders. If it is concentric, there is only 2 points. Concentric cylinder, if rotor is concentric here, then what will happen? Only 2 points, top volume, bottom volume. You cannot get compression expansion. Turbo compressors, people know all these ideas, and mechanical engineering is taught. So, 3 points are required. By offsetting, there is one increasing volume. This is an increasing volume because it is not yet crossed, volume is connected. Once it crossed, then it got isolated volume, and this isolated volume further rotation will go through the exhaust. Now, volume is reduced. Originally, these molecules are suction side. Now, finally, molecules are coming to the exhaust side. This is possible because compression, this is expansion, then isolation, then compression. Expansion, isolation, compression, that is all. That is called rotary vane, whether it is a turbo pump or any pump, it is same, principle is same. So, that is why I show only one pump, and it is this pump only. And it is an out case, it is an oil that is filled because any compression produces heating, any expansion produces cooling, is it not? Any expansion produces isentropic expansion, adiabatic expansion, and isothermal compression. That is the starting principle of heat engine. If you reverse it, you will get refrigeration. So, expansion produces cooling, and always compression produces heat of compression. So, that has to be removed by oil. Oil acts like a coolant, and whenever exhaust valve is opened, when the pressure is more than atmosphere, you have sucked at 10⁻⁻1 tar and compressed it all the way by reducing P1, V1, P2, V2 to a dead volume, and the pressure is 762 tar plus the hydrostatic pressure, the valve opens, then it exhausts. But these molecules are originally at vacuum. So, we are positively displacing the molecules by a eccentrically located. Eccentric people work much better. Most of the scientists are eccentric. very top ranked scientists, they will not talk to anybody, they are very mad case type thing. They will understand the original fundamental principles. Okay. So, same thing here, eccentric rotor will start rotating in such a way you will get compression expansion. Twice it happens for every rotation, and multiplied by number of rotations 2 into V into N is the pumping speed, because N is per second per unit time, V is the volumetric unit. That is all. What is the speed of the pumping speed? Liters per second. Okay. This is not mass, it is only volumetric flows. Okay. Volumetric flows are related to mass flow rate by multiplying with density, that is what we think. But in vacuum technology, they do not multiply with density. Who will measure the density of these and all? It is not liquid or solid. So, what they do is they multiply with pressure, because they know very well, they are more intelligent than us, pressure is proportional to density. For a given thing, pressure is proportional to density. That is why P is equal to NKT, as number of molecules are less and less for the same volume, N by V, it is proportional to P. So, P reduces 100 times, exactly number of molecules reduced 100 times. That is why ideal gas law valid, P is equal to nRT is highly valid for vacuum technology. Okay. So, this I hope you have understood something. So, you will get 10 power minus 2 torque. This is a Rotary Club member, rotary vane pump, most popular pump. This is there always, because you have to start from atmosphere, and this fellow has removed 99.999% of the gas. Where is 760 torr? Where is 10 power minus 2 torr? Already P is equal to NKT. P has gone down 4 orders of magnitude, N has gone already 4 orders, that means 0.01% it has come. Very highly pure, no, it is not at all pure. 10 power minus 2 torr, if you put semiconductor physics, it is not semiconductor, it is bus conductor only. Nothing happens. Okay. So, this semiconductor physics requires 10 power minus 8 torr. Who does that? Normal gas physics is no more valid. These are molecules. That is why we use turbo molecular pump. This is viscous pump, rotary vane pump. These are all dragging gas, sucking, sweeping, throwing, compression, expansion. More than that I do not want to explain, because I take 4 hours to explain the machine theory behind it and all. Then how to connect the rotor, seals and varieties of mechanisms, and what is the role of oil. Oil acts like a lubricant. Inside this lining has to be lubricated, because there is a wear and tear here, friction. Whenever a suction opens, exhaust valve, a drop of oil comes by virtue of gravity. It will be churned back again. So, in this going up and down, there will be a layer of film. That film layer will work like a lubricant, and the entire thing gets heated up. The heat is removed by the fins attached to this, that is called coolant. And here in the top seal, because this is coming at minus 2 torr, going at 770 torr. So, there is a pressure drop here. So, it should be sealing. This is a volume, if it is shorted to this, then it will be circulating. So, that is why oil film will be acting like a sealant. So, what is the role of oil in a rotary pump? Sealant, coolant and lubricant. And you may think that how this oil seals so much, because it is a micron gap. Any small oil film, it looks like a small weak film, but if it is kept under submicron gaps, it will almost like a solid. It will have the flexibility of liquid, but it will seal against the pressure gradient. So, that is why this is called hydraulic seals. Okay. So, these are all known facts only. Depending on the viscosity and other things, I am not going to the details of it. And if you want to see little bit, I do not know, I am not good in computers. I can tell you how to make computers, but not know how to program computers. There is something rotating. So, molecules are coming from your semiconductor chamber in a high vacuum laboratory in CeNSE somewhere here in the IISc Bangalore. They are coming here, because they also would have started from 1000 torr only, 760 torr, and it is behaving like a gas now, coming here, going here, then isolate. Okay. You can see all these animations virtually in your many Google is the best boss, he is the best teacher, but you should know how to search. That is why research is always search first. I hope you got some idea. Okay. Now, after first stage, a level of vacuum will come even after compression it is only 100 tar. Then 760 tar it cannot open. What to do? You connect to suction of another fellow. That is called two-stage pump. Now, that fellow will think that there is an IISc Bengaluru whose atmospheric pressure is 10 power, it is only 20 tar. So, 20 tar I can easily expand, where exhaust valve opens. So, that 20 tar is created by another fellow. So, real IISc is here, but it thinks that is the ambience. So, 2 stages. Then you may say, sir, 4 stages you connect. No, oil vapor pressure is much more than the vacuum created. So, oil itself will evaporate and spoil. Special oil called SP oil, that is called spoil. Okay. So, we have to be very careful about using oily pumps. In ultra high vacuum, now same applied materials 20 years back they were using oil pumps, diffusion pumps, varieties of things. Even scanning electron microscopy also a diffusion pump. Today they all said they dry pumps, because oil vapor, hydrocarbons also will impurify. All oils are organic. LCD, CVD, they may like organic, but semiconductor people don't like organic things. Any organic thing is a nuisance for them, but for us it is a nuisance. Okay. So, we have to be careful when you use oils in a vacuum technology. And for example, food technology, they don't mind 20 tar, 100 tar, but they don't want oil trace. You can see even a small smell of kerosene, one drop in 100 liters you had, you can easily understand that this food is not good. Because our sensors are much better than infrared sensors. Okay. So, we know how to understand. Oil is not allowed at all. That is called edible oils or lubricating oils. Varieties of oils are there. Best oil, special oil, that is called spoil in vacuum technology. And how to do that? That and all lot of problems came. And there was 20 years of time where semiconductor stopped. It's a jokey story, but it's okay for the understanding. Rainy season, all the semiconductor companies are closed because water vapor everywhere. And if you open something and see your chip, etc., and then already a lot of moisture has gone into that. And next time when you evacuate by 20 tar, water vapor which is there on the all the surfaces, they start evaporating. And that will take 10 days to bring it to. First you have to remove vapor, then you will have to remove nitrogen, oxygen, then only you will get vacuum. Then if oxygen is very, very low, then you put boron, nitrogen, whatever, you make it P-type. That stage will come after 12th day. But we want it in 1.2 hours. Your boss had said already production started. No, it has not started. So people said, rainy season, sir, please give us LTC. We will go. Close the company. It has happened. 20 years, nothing. Because, and one mechanical engineer like you, very intelligent scientist like you came, what they said was like a homeopathy dawa, you try to make it still bad and then solve it. How to do? He has let in some dry air in the exhaust stroke, then added some additional dry molecules so that moisture does not reach its saturation. When vapor molecules reach their saturated vapor pressure, when vapor pressure is exactly equivalent to saturated vapor pressure, then condensation dew point works. Otherwise, before dew point works itself, it is floating with unnecessary some friends which have been intentionally introduced by air blast. When dry air is blasted inside to make confusing to these water molecules. So, water molecules are floating. Otherwise, they would have condensed by the time pressure rises to, if the total pressure is such, the partial pressure is more than the saturated vapor pressure, it becomes a drop instead of vapor. That chemical engineers know very well. Okay, what is called dew point, what is relative humidity, and all these things. So, here that is what has happened. And that fellow, one fellow created this very small, one small mechanical thing, 100 rupees solution. And immediately 2 months leave was stopped. Immediately people are coming to the companies and started working because moisture could be removed. After 2 hours of evacuation, when totally moisture has gone, now only dry, at that time you close this. Now you will get -2 tar. So by that time, if you are not a good vacuum expert, what you will think, sir, 10 tar is coming, I am not getting good vacuum, I think something wrong with the rotary pump, sir, you please send it to the manufacturer, they do something, you make a phone call, he says, I am in Mysore, I will come tomorrow, and by that time we will come, sir, it is a rainy season, I got fever, liver, and many problems. So nothing happens, but actually there is no trouble. pump is nicely working. All the way he comes here and says, my pump is working. I am closing on the blind flange. I am showing -2 tar. Your system is problem. Okay, give me 2,000 rupees, go. Now, who will repair it? You will have to repair it. How do you know whether it is a water problem or whether it is a leak problem? That is called troubleshooting. So, a vacuum engineer has to play a lot of roles. Production of vacuum, measurement accurately, design the system so that minimum cost. You cannot make a vacuum chamber with 1 crore rupee. It is a -3 tar. The pumps are all only 10 lakhs and chamber is 1 crore, not possible. But if it is a very high quality, 10 power -9 tar, for example, atomic force microscopy or very high level of experimentation going on there, then you don't make a chamber out of welding brazing. You make like a Ajanta Ellora caves, you take one aluminum piece, cave it and make a chamber. So, no joints anywhere. They are called monolithic chambers. They are used now in applied materials, 2 tar. Afterwards also you should run the pump because something is leaking, that has to be taken care. So, pressure is not changing, but still you have to run the pump. You have to keep the frizz on when you came for the